session. Okay, to the first session, the data rescue. We have 5 speakers, 5 talks, and then 2 posters. So we have 1 more minute. So the first speaker is Anita Paul from TAMK. She will be speaking about the digitalization of data series of Klagenfurt. So Anita, if you are ready, the floor is yours.
Thank you, Dubravka. I'm ready and I'm sharing my screen. I hope you can see it.
Yes.
Okay. So. Okay. So thank you, Dubravka, for your introduction. And my today's talk is about digitalization of long time series Klagenfurt. And it was a collaboration and cooperation with our customer service office in Klagenfurt. And we are doing some work at our institute here in Vienna. And yes, the motivation behind this project was simply that we need historical data. We have to focus on the increasing interest of the public. And here we have a good paper, a new paper. It was published in Geoscience Data Journal, and it is from Shimani Barbara, and we worked on it in a good cooperation with Ingeborg, with Mark, with Matea, and Dubravka. And it was about data rescue in selected countries in connection with the EUMETNET data activity. So yes, out of this paper, it is a really interesting sentence, and it is true. Increasing interest in climate change leads to an increasing urgency of extending existing time series back into the past as far as possible. And with our data rescue time series Klagenfurt that starts in 1830, it is absolutely a candidate station for a long time series in the WMO project Centennial stations. I think Jose already mentioned yesterday in his first presentation that is really important to have long-term measurements that are the backbone of both of weather forecasting and climate science. And it's highly important that we ensure the long-time sustainability of these measurements. So what we want is to implement this Klagenfurt time series that started 1830 and goes till now, which has a resolution of daily data in this project, in this WMO program. When we have a look at the layer, at the card of the WMO website, we see that in Austria, and we zoom into Austria, we have already 6 stations that are there published. And we wanted a 7th one, and this would be Klagenfurt, that is situated here in the south in Carinthia. If you click on one of these green dots that are already implemented in this project, you have more information about these sites. For instance, here Kremsmünster, which is the longest site we have already in our database. It starts in 762. And yes, but we have on this web page, no information. It is if it is monthly resolution data or daily resolution data. So, but Klagenfurt is daily resolution data. So from 1830 till now, we have really daily resolution data and without great gaps. The only other station that we have in our database already digitalized is, and data from 1830 is from Vienna Astronomical Observatory. And what we got from our colleagues in Klagenfurt are climate data sheets. These climate data sheets were bound into books and stored for years and years over in our archive in Klagenfurt. And these climate sheets have observations of precipitation, temperature, wind speed, direction, snow pressure, and relative humidity. They were transferred to our institute in Vienna in 2019. And unfortunately, we started with the digitalization. We started with the digitalization as soon as we could, but 2019, you all know, and 2020, there was, due to COVID, many lockdowns in Austria, and we could not perform it so fast as we wanted, because we have to image. I'm sorry, there is somebody is loud. I hear some noise in the background. Could you mute you?
I'll fix it. Yeah. Thank you.
Okay, thank you. And we transferred it. Yes, and due to these lockdowns, it was not possible to digitalize or image this with our book scanner. The method and concept of data rescue is always the same. We need metadata. We're doing a data inventory. And after that, after these informations, we start to digitalize. So in general, imaging, converting, and correcting. And what is really, really important in last time is the data access. We have new EU and Austrian open data and public sector information policy. So that means in general, we have to publish all our data in a data portal for the public. And so everything will be opened to the public, and everybody could analyze and have a look at this data. Metadata. This is the station history of Klagenfurt. You can see there were many places where the measurements took place. We simply sum up this into two main stations in Klagenfurt State Museum and Klagenfurt Airfield Airport, where we still measure. What is a really, really good thing is that we have overlapping measurements of a period of overlapping measurements from 1950 to 1952, which is sure a good thing for homogenization and analysis. The data inventory was done year by year. So every single year and every single monthly, I think my colleagues did it too, we have the data positions, we have the measuring instruments, we having the observer names, we having the measurement parameters, because there were often changes, and these changes are now well documented in digital form. Further, we regrettably there is many red, but we having a list where we having our process. So what is done, what is in process, and what is already imaged. And I hope the next time if I present this time series, everything is in green. Yes, the image of the climate sheet was performed with our book scanner Microbox Mosquito A1 with 2 cameras, and we transferred this into TIFF with the software Tocosa. What we planned next year is to use the software EasyScan Professional, but we will see how good the new software is. For converting it in OCR readable versions, we use Transcribus software. Now we are running some tests with Tesseract, but the detection rate is currently at 30%, and we're not so satisfied with this. so our aim is to do everything, if possible, to do it in a simple way and learn the program to encrypt the handwritten passages or pages to having an automatically detection, and we could automatically get it in our database, but it's really hard work and the program learns not as we want. If here you can see such a climate data sheet from 1830 at the State Museum, the observations from a State Museum, and this is really not OCR readable. It is written in current. It is a handwriting. It is a bad handwriting. There are some additional informations not in tabular form, and this could not be authenticated or detected by a program. But all this information, how really challenging this is to detect, you can the information about this is in this paper I given you in the first slide as information. There is more information about that. So OCR readable partly is this sheet. It is from 1938 and from Klagenfurt, Wetterwarte, and here OCR readable are these parts, but the handwritten part is not OCR readable till now. So a colleague of me is doing some work on automatizing and learning the program to detect this handwriting tables. Tables are really hard to get into database, but he having a cooperation with the technical new university in Vienna, and perhaps it is possible to automatize some things there. Yes, and the challenges, as I mentioned, are still the current handwriting of these old scripts of these old measurements, that we have other measurement methods, other times, other instruments, other units, and so there is a lot of manual work behind this still. And yeah, and we having to manpower or woman powers personnel in our sections that are performing this and keying this. And here is a sample of such an sheet or metadata sheet, metadata information written in current, and we having two experts in our section that are really good in current, and are encrypting always this current. And so we have a translation here in German. This is in yellow, and I translated it in English. And if you read the English text, it is about weather abnormalities. So the barometer average in June is tiny in the month of March, line above variable. Otherwise, every other 5 months above, line below variable. In January and February, the temperature were very low, but April and May were 2 degrees above normal. There was a lot of rain in June. It is not really English. I think everybody will now think about it. These are not English sentences, but I can reassure you, it is not really German too, because the translation is it was another kind of German in these years as it is now, and so we're doing our best to translate it in something what is really understandable. Now, on the right-hand side, you can see other metadata information. Here we're having some observers listed that are that have done this measurements in this time of this climate sheet. Yes, and one thing is the visualing tool. Here we having a colleague of me programmed a tool that is very helpful, and so we can see these image data sheets and having a really easy access at this data sheets. So with one click, you can you can call these sheets. Yes, what is the future? We want to digitalize all the relevant data. The digitalization of TIFF files with OCR software. Not plausible values would be corrected, are corrected. It is really important to having some sort of data quality control and adjusted on the time period, because data quality control in 1830 is another data quality control as it is now. We want to publish this long Centennial time series Klagenfurt in the WMO program and via our data portal, via our ZMG data portal. And this data portal will be soonly available at our homepage. And here you can see the two our team at Carinthia and in Vienna. And yeah, just if you have time and you are interested, have a look at our homepage. There are more information. And for contact, you can contact me via my email address. So thank you for your attention, and yeah.
Well, thank you, Anita, for this very interesting talk. And now we have time for some questions. You can raise hands in this down of the screen.
Are there raised hands? I don't see it. Yes.
Yes, Monica.
Good morning, everybody. Thank you, Anita, for this presentation. Oh, my camera is not in the best position, but no problem.
Okay.
So my question is, how do you prioritize what to digitize first? Do you have a team for decision, or do you ask, or can you get an advice from a climate department, or?
Okay, yeah. You think the time series Klagenfurt or in general?
In general.
In general, we're digitalizing after priority. So first we look at how long the station is, how long the time series is, and how good the quality is. Sometimes we're having climate sheets where everything is in red and corrected and a bad quality. We doing at the priority, we like to have also time periods that are not where the quantity of the data is not high. So is not high. So mainly in the period of war. So the First and Second World Wars. In this period, if we have some data, we do the priority there first.
Okay, and do you have a request, for example, from climate department to digitize the project, for example, or?
Yes, this is the second thing. If there are some projects or needs for some data in this area or some specific questions about areas and or needs for data quality control, that we need a higher number of stations there, of precipitation stations or measurements, then we are doing this first. So this is the other point. Yes, you're right.
Okay, thank you. Thank you very much.
Mm-hmm.
Dan, please. Yes, I can see you.
Thank you. Good morning. Thank you for an interesting presentation. I was just wondering whether in Austria there was any, whether you ever used sort of citizen science projects for digitizing historical records. So we've had some success of doing that in the UK, where you get you know, enthusiastic volunteers to do all the hard work. So
I know
did
about
anything
this.
similar. Yeah,
we did something about that in the phonological. So the phonological,
okay.
we having some classes and pupils who are very interested at this and did some work with this. But you need an expert for digitalize, just for digitalizing. You need experts, because a pupil or some volunteer would not could not recognize or write or read current, yeah. And there are really something, there is information in metadata and current you don't know what there is. Oh my god, the barometer, you have to correct it, correct this information. And for a volunteer, I think it is really hard to know what to do then. Or the information about temperature, it is measured in Remu and not in Celsius or so. Yeah. And then you have to calculate in new sums, and afterwards it is more work than we have. We have you know.
Just adds to the problem. Yeah.
Yes.
Okay,
but we thought about this, and we thought about it in the lockdowns. Many people were at home, and this could be a good project, really. But as I mentioned, we need a little bit of methodological background and expertise. Okay.
But as I say, I think we have had some quite good success with some recent projects in the UK. I'm not directly involved, but I think maybe on the right platform, as it were, it tends to attract people who have an interest in the weather and climate, and perhaps they may not be working in the at the Met Institute, but they have sufficient background knowledge to do a reasonable job. But okay, good, thank you.
But I think in Ireland there was a project that they're doing some students for meteorology a double keying. So it was keyed, and they double keyed the I think it was Ireland. I heard there was a talk about this, and this I think this was a good thing.
Yeah.
Okay.
Okay, thanks.
Okay, thank you, Anita. And now we have a second talk, which is about data rescue and digitalization of historical wind speed observations in Sweden. So, Eric Engström, the floor is yours.
Thank you so much. Then I try to share my screen also. Can you see the presentation now?
Yes.
Good. So I'm very happy to be able to give this presentation, and it's about a project in Sweden that is a cooperation between the Meteorological and Hydrological Institute and the Gothenburg University, and also the Spanish Research Council. But so I start right away, and we will come back to this in the presentation. So we'll see. So here is some of the colleagues in our institute, and also, as I said, Gothenburg University, and also the Spanish Research Council that is participating in this project called WindGust. And it's founded by the Swedish Research Council for Sustainable Development. And some of the background and the rationale for this project, changes in wind climate can have a lot of different effects for the society and the environment, and especially extreme winds can damage infrastructure, agriculture, forestry, and buildings. And also wind energy has a key role in the transformation to a sustainable fossil fuel-free energy system. So it's different aspects. And this project called WindGust is, as I said, a cooperation between 3 different organizations. And the aim is to fill this gap of wind data earlier in our records or observation history, and improve then the knowledge of causes driving the wind speed variability and in Sweden. So the project is the full title in our application is Assessing Centennial Wind Speed Variability from a Historical Weather Data Rescue Project in Sweden. And we started this project in the spring last year, and met with the different participants in the project. And it's composed of 3 different work packages. The first work package 1 is about digitalizing and rescuing wind speed data from our archives here in our institute in Sweden. The second part is about quality control and homogenization. And the first part we did in our SMHI, the institute, and the second part will be led by Gothenburg University, and it's a cooperation then between all partners. And the same case with the third part, that is then assessment and attribution of the historical wind speed trends that we see when we analyze the data. And we also publish and communicate these results to the society, as I do now in this presentation. And here you see a map over Sweden with the weather stations that we digitalized in this project. So it's 12 stations in different places in Sweden. And as you see, it's mostly coastal stations and in the south of Sweden. So it's not really evenly distributed, but this was a station that had data, instrumental wind measurement data, very early in Sweden. So we wanted to prolong the available digitized data backwards in time. So in this project, we digitalized data from 1920, 1930, and 1940 for these stations. And here's a picture from our archive where we have the paper journals, and you also see a view of one of the journals. We digitalized both wind speed in meter per second and wind direction with a resolution of 32 different directions. And so this each page like this is 1 day, and each book contains 6 months of observations. And it's not only wind speed, but we digitalized wind speed in this project, but it's also temperature and precipitation and so on. So we have more to digitalize in the future. So something about these historical wind measurements. as I said, it was mostly coastal stations, so the anemometers were often mounted on the lighthouses or on a freestanding mast. So they were, nowadays we do the wind measurements at 10 meters height above ground level. But in these cases, if they were in the lighthouse, it could be 30 or 40 meters up above ground level. So it was different heights. And here you see the red circles where the anemometers were mounted on different stations in this project. And there were also different instruments. To the left, you see a very early type, a Kruger instrument, where the wind pressed on a big screen. And then Hageman, where the wind caused a low pressure in the tube in the instrument, and then the observer could read the wind speed. And then to the right, the Sandström anemometer. And the two first one we haven't used so much data from because they were used very short time. But then with the Sandström anemometers and the similar after that, they were more spread in the stations and used over longer time. So that's where mostly from these kind of mesh instruments we use the data. And here you see the number of stations for each year that are digitized in our database called MORA for our observational data in Sweden. So it's all from 1925 until now. And the red square was the data that we digitized in this project. So we could get now about 20 years more of data, and totally with all the station it was, I think, 150, 160 years of data that we digitized. So how did we do it? We brought up these weather journal books from the archives, and we scanned them to make PDF files. And then we put the books back in the archive. And on this picture, you see the observations for 25th of January 1925 from Haparanda, that is very far north in Sweden. And because then it was during the pandemic situation also in Sweden, so when we did this scanning of the books, then the digitalization could be done from home if the operator preferred that. So that was a good thing with to solve this problem during this hard time. And then the digitization was made in a digital template that you can see now in the picture. And the design was to mimic the design in the paper books. So it would be very easy for the staff to put in the numbers in the right place in the template. And when they did that, the values were directly stored in our database. So some challenges and experience from this work. The paper journals was mostly in good shape, even though they were often 100 years old. In some cases, it was data was missing or the handwriting was difficult to interpret or to read. The scanning, as I said, had to be done in the office because we're not allowed to take these books out of the building. But they could digitize the numbers from home. And some, if we found suspicious values, we could check them an extra time. And you can also see the scanning equipment we used for this work. And it was very good to be able to operate the scanner with a foot pedal, so we could have the hands free to turn the pages in the book. But it was a very static working position to do this, so it was important to take breaks often. And sometimes the scanning had to be redone several times to get the needed quality of the picture. So how will this project now continue? In the next work package that is starting now during this autumn, the data is quality controlled and homogenized, and this will be led by Gothenburg University, and they will use Clima-tool method developed by Jose from Spain, and we will use reference data sets, gridded reference data sets such as ERA 20C, or also in Sweden we have eustrophic wind data that we could also use as reference data. And then it's also good that we have these scan PDF files, because it's important in the homogenization work to be able to go back to the original information if we find something suspicious. So then it can be accessed from Gothenburg University. And then the third work package will be done next year, also led by Gothenburg University. That was my whole presentation. So thank you very much for your interest, and I'm happy to answer questions if we have time for that. Thank you.
So thank you very much, Eric, for this interesting presentation. Yes, we have time for some questions, so go ahead.
Should I stop to share?
Yes, I guess, because I can't see participants. Yes, Isaac.
Hi, Eric. Good to see you.
Good to see you.
I would like to ask, which parameter of the wind did you scan and then you wish to explore later? Is it gust? Is it average wind speed? It was hard to see what was written inside the books that you are scanning. I saw that there are different times maybe, but I didn't clearly understand which parameter we are looking for.
Yes, so in the book, the observational time was, the observations was done several times during the day. So at most, I think 6 times during the day, but it varied between maybe 3 and 6 times a day. So, and the parameter is I think it's some average wind speed, but it's in the early times it could also be momentum wind speed, so it's maybe more like wind gust than in that early time. But it also depends on the construction of the instrument, how the reading was done. So yeah.
Mm-hmm. Okay, thank you very much, Eric.
Mm.
Well, I can't see more hands. So are there more questions? If not, we can move to the next speaker, that is Stefan Bronyman. He will be speaking about the rescue of 18th and early 19th century global meteorological data. So Stefan, the floor is yours.
Okay, thank you very much. Can you see my screen?
Yes, yes.
Great, okay. So in the next minutes, I will present you results of two projects, Swiss and Global Meteorological Data Rescue, focusing on the 18th and early 19th century, work that we have done in the ERC project PaleoRA and in the Swiss GCOS project Long Meteorological Series. So I will start with an inventory in which some of you were involved, and that started as a way to prioritize data rescue activities in Switzerland and globally. Then I would like to present what we have actually digitized in Switzerland and globally, then examples of use of the data. And if I have time, I would also like to introduce you the Copernicus Climate Change Service Data Rescue Service, which may be useful for some of you, has useful tools and useful hints on data rescue work. So all of this started at the workshop in Bern in 2018, where some of you were present, when the goal was to compile an inventory of everything, or as much as possible, that has been measured globally prior to around 1850. We said 1890 for Africa and the Arctic because of there is not much before 1850 in these regions. And so the participants of the workshop helped to compile a global inventory that was then published in BAMS a year later. And this is just two maps from this inventory of stations, regardless of whether they have been digitized or not. Globally, on the left plot, you see it sorted or colored by the starting year. On the right side, by the length of the records. Obviously, we have lots of records and early records and long records in Europe, also in New England and some other regions of the globe. And then it gets worse. You can see, especially South America prior to 1850. We have not very much. In Africa, we have a little bit, but that's mostly between 1850 and 1890. We have data from Asia, Australia. So this was the starting point to have an overview. We had several thousand entries in that inventory, and this helped us really to prioritize where can we have the best, the greatest benefit of digitizing additional records. Is this the early times? Is this in the 19th century in Asia? Or where is the best benefit in the Caribbean, etc.? Another interesting finding from that inventory of early instrumental data, for me at least, was the time evolution of the number of series that we had in the inventory. This is shown here. The number of series has not really a scale because it's also hard to capture. How do you treat like individual variables at one station? Sometimes you don't even know that. So this is just a number of entries in our inventory. And what you can see is that it starts in the 17th century, and you see the early Enlightenment scientists around 1700 contributing to a slight increase, early compilations. And then we have the high time of the Enlightenment in the 1780s. We have the foundation of the Palatina Society, for instance. So we have a peak of the number of series globally. And then we have troubled political times with Napoleon, the coalition wars, etc., leading to a decrease of the number of stations globally. The number of the 1780s is only reached again in the 1820s. And then we start to see this big increase also with the rise of telegraphy, the national weather services, etc. So I think climate data also tell us a little bit about world history in that instance. But let's go now to the projects. So at University of Bern, we have two main projects. The one, as I already said, funded by GCOS Switzerland, focusing on long series. In that case, we want to have sub-daily data, so the individual variables of all variables we find for the very long records in Switzerland. Meteo Swiss station network starts in 1864, and until now there were only 3 longer records that have been published from Geneva, from Basel, and one from the Camp Saint-Bernard. The other project is focusing on the global scale, trying really to get as much information as possible on a global scale, but focusing on monthly data. So in that case, if monthly data were already available, we prefer the monthly data because it saves a lot of work. But very often we have digitized also sub-daily or daily data. And again, all variables were digitized. So let me just show you some examples. Also for Switzerland, we started with an inventory and finding that there was much more data around than we thought. We found over 300 records prior to the start of MetaSwiss in 1864. Many are short, but also actually quite a number of long records. So if we speak about 200-year-long records, there's not just the 3 records I just mentioned, but we could do maybe a dozen such a long series for Switzerland, and we have done that. We have done some additional long records for Aarau, St. Gallen, Zurich, etc. So we have increased Schaffhausen also, so we have increased the number of records. It also helps for the long record. So this is the example of Basel, where the standard record, the long record going back to 1755, is composed of mainly 2 observers actually prior to MetaSwiss, both measured for a very long time, Dannone and Merian. But if we go to the archives, we find many more. And so these series, they could help to fill gaps. They could help to check the other 2 series, which maybe I'm sure that the 2 selected series are probably the best in terms of quality, but there's so much additional information we can gain from digitizing all records from Basel and not just the 2 most prominent ones. So that's just the example of Basel. Now the example of my hometown Bern, there has been actually no data available from Bern prior to the start of MetaSwiss, but if we go to the archives, we find that we could do a record almost all the way back to the 1750s if we use Neuchâtel for the first few years, which is about 30 kilometers away. So probably we don't do that, but still we can go back to 1760 with data from Bern. Here it's more than just 2 observers that we have to concatenate, but we have many segments from many different observers, but fortunately all overlapping each other so that we can do a long time series of 200-250 years from Bern as well. And the same is true for other stations in Switzerland. So we can do new series of temperature and pressure. Another example is Zurich, with the oldest series that we have from Switzerland. Here what we look at is sub-daily pressure data from 1708 to the 1730s, measured by Johann Jakob Scheuchzer. We also did some reconstructions that are shown as a blue line. And there are missing values here, missing periods, even though the observer measured, I think, throughout the entire period. We do have things like the annual minimum and maximum pressure for the entire time period. So he was measuring, he just wasn't publishing the data, and they cannot be found in archives anymore. So maybe the first year of pressure is a little bit low, but at least from the 1710s onward, we find useful pressure data from Zurich that we can use to do climate research. We also have temperature data from the same person in Zurich. That is very difficult to deal with, no real scale. And we digitize the data, but we don't do anything at the moment with temperature. We do work with rainfall data, precipitation data from the same observer from Zurich, also going back to 1708. Here it's a little bit extended with a later observer, and compared with the long series from Paris, we find an amazingly good correlation with precipitation in Paris for this 50-year period on the scale of monthly mean values. So we have found actually quite a large amount of additional data that have not been digitized so far. Here, in that case, we digitized the daily data. That's the Swiss project, which lasts until March next year. And by that time, I hope that we will have published all of these new Swiss series. Now let's go to the global project. Again, this was guided by this inventory, and the goal in the end is really to do climate reconstructions on a monthly scale. And since many monthly data sources have been published, especially also early compilations done in the 19th century that contain all the data from the 18th century, this was an easy target. And so we digitized lots of these monthly data, but we also did lots of sub-daily data. And the focus was on overseas data or on very early European data that we thought have the best benefit to do global climate reconstructions. So a number of problems or thoughts in the early days. One obstacle was publishing the data. We very often do not find the original data, and publications often do not contain the individual values. Later on, it was custom to publish the monthly averages, but in the early years, in the early 18th century, most or many observers published the monthly maximum and monthly minimum pressure, for instance. Can we even use that data? Well, we digitize it because it's not much work to digitize 1 or 2 values per month. And to our own astonishment, we found really a good correlation with monthly mean values if we simulate the same process in recent years. So we even digitize just these monthly minimum and maximum pressure, at least for temperature. It doesn't make much sense. So we have also these data in our data set. Let's look at a few numbers. This work was done by Yuri Brunyara, coordinated by Yuri, and performed actually by many student assistants that helped with digitizing. On the left, you see the number of digitized records. So one variable at one station would be one record that we have digitized for this project. Overall, it's far more than 1,000 records that we have done globally. We have done temperature, pressure, precipitation, but also wet day frequency, and what is labeled with others includes wind and weather, sky, etc. You can see that there are spikes in this in these time series. We see the very early attempt to compile global data by the Royal Society, James Turin, by Clonold from Breslau. So there were early networks in the early 18th century. Then we see this huge spike in the 1780s, where we have the Palatina Society operating the global or intercontinental, I should say, measurement network. We have the French Society of the Doctors. They operated a network. We have the Toaldo network in Italy with a large amount of precipitation data. So this is a really very well covered time period where we could do excellent global climate reconstructions and even weather reconstructions. Then for the 19th century, we have the collection by Heinrich Wilhelm Dove. This was all of that in the 19th century was printed and can be downloaded on PDF files, so it's easy to OCR these data and to include them in collections. In the middle, you see the split by resolution for temperature and pressure, and you can see that a lot of that is monthly, which is an easy target. And of course, you also have daily and sub-daily data, mostly sub-daily. On the right, you see the split by length, and this shows you that by far the largest amount of records that we have is shorter than 10 years. So we are dealing here with short records that have up to now not been the focus of climate research. Everyone is focusing on the very long records, but we have hundreds of very short records that we could also use for climate reconstructions. Just one example, we have also digitized the Palatina data, a very famous data set, which for some reason has never been published in full. So we have digitized the sub-daily data during some years where I guess the funds were running out or so. We also, the data were published in daily and monthly averages, which we also digitized. And these data were also then used to do daily weather reconstructions for the 1780s. It's just one example out of this big collection of data. Now, a lot has already been done by others, of course. We have all the work that you all have been doing, all the work that all the publicly available data set. And if we now combine our own rescue data with everything that is available and try to produce a data set that has only series that go back prior to 1890. This is shown here. This is work in progress. This data set is being uploaded right now to a data repository, and we are working on the final draft of the paper on this data set. But you can see that it will have approximately 12,000 monthly records in it, all of which go back prior to 1890. So actually there is a lot of data out there that can be used for climate research. But as I said, many of the records, a very big fraction is short. So just some examples of use. We use these data in our group to do climate reconstructions using data assimilation, combined with documentary data, clearings and everything. We also give these data onto data sets where they can be used, for instance, for dynamical reanalysis, like the 20th century reanalysis. And we also do daily weather reconstructions for Switzerland with an analog approach. So I guess I should hurry up. I will upload the slides to the conference so that you can have the links here where to download the data. I just would like to spend the last 2 slides on the Copernicus Climate Change Service Data Rescue Service. This is a service really for you who are doing the data rescue work. It has metadatabases on projects, on inventories. It has tools, metadata QC. We suggest a common format that facilitates the QC, that facilitates data exchange and facilitates ingestions of the data into global data set. It also has best practice guidelines. And maybe one thing to highlight as the last slide, there is also on this website the data rescue facility. This is a job dispatch system where you can upload PDF files and manage users, digitizers. So you can give the files to the digitizers. They can upload their digitized data back to the system, and you can manage your entire data rescue project through this website. Okay, so a large number of series would be still available globally, mostly short. Many have been digitized, but many only on monthly means so far. So what we have done could all be done also on a scale of individual values. And we do global reconstructions and daily weather reconstructions for Switzerland and Europe using these data. Okay, thank you very much for your attention.
So thank you, Stefan, for your very interesting talk. And now we have a few minutes for some questions. Well, I have one question. Do you have any metadata about these old measurements? I mean, about sighting and instruments and etc.
Not very much. So we have a little bit of metadata, but since a large fraction of the data is taken from collections, there is not much metadata. You know the inventory, you have also been part of it. So this is one source of information. For the Swiss stations, we go much deeper in terms of metadata. So Yuri Bruniara especially is compiling the necessary metadata, but we cannot do that on a global scale. So unfortunately, we just have what we have, and we cannot go to. So what we find in our sources is that we have, but we don't go to archives just to get metadata. for series where we don't have the metadata.
Yeah, thank you. Well, it is reality, unfortunately, because with metadata we could have much better conclusions about measurements and results, but we can't do a lot about that. Even, I mean, in Croatia, we missed a lot of metadata, so on a global level, it's even worse. So if there are no more questions, I can't see any hands, then we can move on. Thank you, Stefan, very much again. And the next speaker is Agnieszka Bibic. She will be speaking about digitization of meteorological data archives from Poland from 19th to the mid-20th century. So the floor is yours.
Thank you, Dubravka. Good morning, everyone. I will try to share the screen. I hope I can be heard by you now. Can you see my screen? Just a short question. Thank you for confirmation. Okay, as Dubravka has already said, I will have a great pleasure to present you the results of the project conducted in Polish Hydrometeorological Service in the years 2018 until 2021. We have just finished the project. You can see here only two names, me, myself, and Zbigniew Usternul, as the, let's say, scientific project parents. Of course, I'm smiling now. But the results I'm going to present are behind the results. There is a huge work, or more than 10 people, the project team, and it's important to stress, to highlight it here. What was the motivation? Of course, the same as already said by Anita and the other speakers. We wanted to rescue the data we have in Polish archives, Polish Met Service archives. We wanted to do it in two stages, let's say, to rescue, to protect the manuscripts, the diaries. It was the first thing, and the second thing, of course, the data. So we wanted to digitize as we understand it. I mean, to make the digital digital database, numerical database. What was the problem? The problem was that our archives is not in a good state. Of course, to the picture to the left shows the archives quite well preserved, but most of them, especially those in from 19th century, but not only, also the modern paper, let's say, is not in a good state. So what we wanted to do is also to preserve, to repair the old diaries, not to lose them totally. As we didn't have enough money, I mean, as the institution, the Met Service, we wanted to apply for some funds. Unfortunately, at the year we wanted to do it, I mean 2017, there was no national or international funds and project calls opened. So we decided to apply for regional funds, regional operational program for Małopolska region, so in southern Poland. It was not a bad decision or the best solution for us, because in southern Poland, there were most of the stations dated in 19th century, dated back to 19th century, were located in southern part of Poland. So the project helped us to rescue a lot. This is our opinion. Of course, you will see the result, and you will be able to decide the amount of work or whatever. Of course, what we had to do is to go through the archives quite deeply. We did the inventory control. We had to check the stations availability, calculate number of pages, because it was the project proposal. So we had to calculate it quite carefully. for both paper preservation as well as digitization, a different number, it turned out. Of course, the manuscript paper quality as well as the collection volume. And what was much more important was to calculate the time-consuming activities, because we wanted to do it on our own. I mean, using women and manpower of National Met Service. So all of the digitizing, numbering activities we wanted to do on our own, as well as the data portal as the result. Because what needs to be highlighted is that because we got finally, and fortunately, the funds, one of the obligations was to open the portal to public. So we have already finished, and it is on the website. I mean, the data portal in which we disseminate the results, and people can use the data. In a map, you can see the station availability. As I told you before, it had to be reduced, limited to the borders of Małopolska region. Or even for Małopolska Voivodeship, but we included also some supplementary stations, explaining that it's from a climatological point of view, it's really important to have these surroundings digitized as well. So finally, we digitized 23 stations with the longest possible data series. Unfortunately, they have, because of our history of Poland, there was no Poland at that time. I mean, 19th century, the beginning of 20th century. So the data series have huge gaps, but anyway, it was the only possibility to preserve, to rescue these materials. So we decided to use also the shorter one to rescue as much as possible. What we managed to do, fortunately, is also to prepare the archive room and the digitizing laboratory in Krakow, because the project was mainly conducted in Krakow location. We bought the scanners, 2 scanners. We managed to buy 2 scanners, one for flat scanning, and the second one I will try to show you. And the second one, it's just the professional one, but it landed. I mean, it was sent to the archives in Warsaw because it was much more useful at that location. But coming to the digitizing process and the project implementation, because of our main aims, I mean, both diaries protection as well as data protection, and for the institution which gave us the finances, the diaries protection, the scanning process was much more important than our activities, I mean, data interpretation and numbering. So the main part was this diary protection, and you can see we managed to repair it. I will show you in a minute. The state of the sheet was quite bad, so it was impossible to start scanning without this repairing work. Then we decided, and we had fortunately the funds for that. These manuscripts were deacidified, and finally archived in Warsaw. And the second part of the work was this scientific part, somehow saying, I mean, making digital images database. It was necessary because of the proposal, and numerical database, which is important for scientific point of view. And I will try to go through all these steps, not going into details, of course, because of the time, but to show you also the final results, what is the already functioning portal. So this first approach, or the first part of project implementation, was this manuscript protection. We managed to get the experts report, the expertise done by the professional paper conserver. I'm not sure if it's the good English name of this person or the job. She did, but it was a professional expert. And what she did was to divide our archives into 3 groups. The third one was of the highest degree of damage that was totally necessary to be repaired. Without this reparation, all digitizing process couldn't have been done. The second group, which was of certain amount of mechanical damage, as you can see in the description, and the first group quite okay, with no need to be repaired. We managed to repair the whole third group of papers, as well as almost a half of this second group. You can see the results to the left. The same 2 pages before and after the reparation process. Of course, the light is different. One is the scan copy, and one is just the picture, but you can see the stage of damage and the final results of this reparation. I mentioned this third group of manuscripts of papers. You can see what I really mean. I mean, we cannot totally, some of the pages were totally destroyed. This is what should be said here. What we managed to do is we had an agreement to separate the pages because a part of this collection was sticked in volumes, but volumes totally how to say it in English, with no particular standard. I mean, different sizes of papers, different years, different, and so on and so forth. So to make this digitization process efficiently, we separated these volumes. What helped both people who repaired, it was professionally repaired outside by the outside institution, as well as in digitizing process. We were able to digitize most of the sheets in Krakow using this flat scanner. The others, the most difficult were scanned outside of the Institute of Meteorology. You can see that almost this is the final number of the copies. More or less 50,000 scans were done. Of course, few of them were repeated. This is what has already been said because of the quality of these scans. The second part of work, of activities, were these connected with creating the numerical database. We didn't even try to use the OCR software to recognize the numbers because the state of the writing was sometimes okay, as here, and sometimes was really badly. So what we had to do was to do it totally manually. What we tried to automate is the first round of validation. We created the simple Excel sheet, even not the software, because of different units used at 19th century. This is what I will show you in the next slide. So we decided to copy the same numbers as we see in the diaries and afterwards to recalculate the units and to do other validation procedures. This Excel sheet was a kind of self-correcting using simple algorithms for extreme values, sub-daily values, as well as a snow cover. Because I should have said it before, we decided to make numerical copies, numerical database for the main elements only, because of the difficulties and the time. We had only 3 years to finish the project. So as for now, we digitize, I mean, we numbered air pressure, air temperature, sub-daily, precipitation, and the snow cover amount. So this is what we have in sub-daily resolution. As I mentioned before, because of Polish history, at the history of meteorology itself, we found out, we knew it, that it might happen. We had different units, especially for temperature and precipitation and air pressure. Temperature was easy because it was in Roy meters or in Celsius, of course. So recalculations were quite easy. The problem was with barometer readings as well as with precipitation. Usually they were recorded in Paris lines, but some other units were also found. As I said, because of our history, there were some Austro-Hungarian inches lines as well as Polish inches and so on and so forth. So it was a kind of interpretation, not only numbering, not only keying, but it was necessary to go through these numbers, this data very thoroughly, not to make any other mistakes. What we had to face up and unfortunately failed finally were the examples of, let's say, unknown units. You can see here the example of two sheets, the same period, different stations. We discovered something that should be precipitation in Paris lines. Let's see here at the second 5 days period. And after the calculation, we were surprised with the amounts. So we had to do the parallel comparative analysis using Krakow station data. The station in Krakow, now led by Jagiellonian University, was established in 1792 with the long data series and almost no gaps. So it was a kind of reference station for us to check the data and to do such comparative analysis. And you can see here in Krakow, of course, the location is different, almost 50 kilometers away from that station in Maków, Podhalański. But anyway, the amount of rain recorded in Krakow and written in Paris lines is totally different. So in such a situation, of course, we have these numbers, we have this data digitized, but we had to get rid of it to skip this information in further process. I will show you what I really mean. What we also did was to go through the station metadata. Of course, it was of the different complexity, different amount of information for different stations. But we did our best to take the most important information from described in the diaries. So we create a table with station location, measuring times, as well as some instrumentals and surrounding changes, observer's name, if it was possible, and any comments that can be found in the diaries. To highlight the changes, you can see the red color in this table, and it's a part of the portal, which, as I said, is already on. So I will invite you in the end of the presentation as the conclusions to go through the data. At the beginning, I told you that we had a few runs of validation. The first one was this self-correcting Excel sheet. Again, afterwards, someone go through the data and checked it once again. Afterwards, we had this unit homogenization or unification. Finally, we went through data quality control procedure, let's say weather-dependent analysis somehow. We checked all these numbered data according to the long-term variability, and it allowed us, it helped us to find out still some bad values, bad numbers, even after the calculations. So we come back to the original manuscripts, checked it again, checked the weather conditions, especially for snow cover and precipitation, as well as for temperature extremes. Sorry for this draft pictures, but it's the part of the analysis just to show you the work already done. And the final stage, which is behind us, is the project dissemination. You can find the portal. I will try to start. Oh, I will not be able to do it. Sorry for that. I will try. What we already did is to put this portal, this final results of our project in the main page of Polish National Hydrometeorological Service with the address given here. It has, I got this morning the information that English version of the portal is also on. We prepared the short film presenting the portal, the database, and the work done. It is in Polish, but with English translation, as you can see. So all the users can focus or can go through the information on their own. What we have already done is to describe the project in IDAR portal as the finished one. So as for project dissemination activities, also this one was done. And the final step, or just to conclude the information, this portal, HistClean portal, presents mainly few or consists of few parts. You can browse the station. As I told you, the 23 stations were digitized in this project. You can download their archives. So this is the main function because of the finances. You can also browse the data. This is what we decided to do, but not in this route, in this draft or the raw version. We decided to calculate the averages and to show to the public the long-term runs of averages, just to make it more nice, let's say, nicer for the users. And we added here also the station metadata, what I have already described. If you go through browse the station part, you will see the history of the station. with some archives picture as well as the station location. Then if you go for download the archives part, you can go through the availability matrix. When you can see all these green dots shows the data, the digital copies availability. You can also choose the station and the year to download the data, either as monthly records or let's say the annual part, the yearbook, but in separate files. This chart or this gross data part is just prepared, as I told you, for public, for the users, non-professional users. You can see the long-term courses of all digitized or numbered weather elements. Here it is in Polish, but I didn't manage to change the picture. But as I told you, it's already available in English. You can choose the elements. Either you can see all of them. There is also the chart of anomalies that try to compare the historical data to the latest climatic normals, 1991 to 2020, again to make people more familiar with climate change issue. And just 2 sentences, I can see that I'm out of time, sorry for being late. What we plan to do during the post-implementation period is to digitize much more stations, broadening the area not only to Małopolska Voivodeship, as I showed you before, but to Małopolska region, as well as to Galicia region, the red one, to cover the eastern part of Poland, which has also some long data series available. The highest dots, these are the data series longer than 40 years. So this is what we are focusing on now. And all these green dots, these are our plans for the next few years. We hope to manage when they are digitized. They will be included into the web portal and open for public. That's all from my side. I will put the web page address in the chat to show you the result, the final results. Thank you for your attention.
Well, thank you, Agnieszka, for this very interesting presentation about the huge amount of work that you've done. But we are out of time, so I propose that we leave questions for the discussion on the session 3 and move on to the next speaker, the last speaker of this session, Mark Prom. He's going to speak about data rescue of climate and hydrologic data from the Catalan Pyrenees. So the floor is yours, Mark.
Thank you so much, Dubravka. I'm going to share the presentation. Okay.
Yes, we can see it.
Okay. Thank you so much. I'm Mark Prom from the Catalan Met Service, and within this 20 minutes, I'm going to show you the results and the project that we've involved for the last maybe 5 years. That has been the digitization of this new documentary data from the Pyrenees that comes from the electric power stations that are installed from many years. And this project has been done jointly with Jaume and Monica, also from the Meteorological Service of Catalonia. The attack plan of this speech will follow this scheme, the motivation of the project, we'll have a look on the historical background of the data, of the origins of the data. Then we move to the data project, that is the main interest, and we'll move in a specific documentary data that it's the hydrological charts, and we'll see the evolution of these documents. And then we'll end with the available meteorological observations and metadata that are available thanks to this research work. So the motivation, I think it has been already said by Anita in the first speech. Actually, this project is closely linked to this workshop because, as you remember, there was a EUMETNET data activity for many years that paid special attention on data recovery in Europe, and specifically the interest of this project was to detect Centennial climate series and also climate series located in mountainous regions. So these were two of the main objectives of the data project, and there is a nice paper that is already available. But there is another aspect that it has been said recently by the last IPCC report, and it said that in some regions, either geographical or typological, mountainous regions, small islands and cities, and for certain phenomena, fewer observational records are available or accessible, which limits the assessment of regional climate change in these cases. So there is another point that supports this project. And finally, as we are located in a mountainous region that is close to the Mediterranean climate, there is an additional interest to have a deeper look on what's going on climate over this mountainous region. So the historical background of the project is closely linked to the electrification in the Pyrenees. As many places in Europe, the need for electricity light to feed the growing population, specifically in Barcelona, and the industry that was mainly textile, increased the number of hydrological power plants in the Pyrenees. And jointly with this growing power plants and dams, several weather stations were installed close to these settlements. And over the years, all these settlements merged into a unique electricity company that it's Endesa. It's the main electricity company in Spain, and this company collected all the documents in a single archive that is now available, and it's the main focus of this project. So the data rescue project, it took a long journey. As you see, it started in 2013, so almost 10 years ago. And it started when the Meteorological Service of Catalonia identified documentary data in this archive of the Endesa Foundation in Barcelona. The first step was to have a first catalog of the documents. As you can see, there is a lot of information there, and the first step was to detect which documents contained climatological observations or meteorological observations. So this was the first step. And after several attempts that were unsuccessful, finally in 2019 there was a collaboration agreement that was signed between the Fundación Endesa Foundation and the SMC. And last year in June, the digitization project started and ended in November. And now we are in the process of cataloging this material that started in May, in May, and it's an ongoing process. And now we are about 30% already cataloged, and we used a software that it's called Artidoc, that is very useful. And this photography is the agreement signing ceremony of the which involved all the partners. So this is a general description of the collection. We have material covering this period from 1922 up to 1992, so 70 years of data. The area that is covered by the data is mainly the Catalan Pyrenees, but there are other sites outside this mountain range. You can see here the volume, 9 linear meters of information, and the number of images that have been digitized is almost 45,000 images that are already available. And there are three main types of documents. The most of the information is present as hydrological charts that contains hydrological, meteorological, and electricity production data. And there is another collection that collects snow depth and ice depth at several lakes in a specific site in the Pyrenees above 2,000 meters. This is a very nice collection, and we will see later on some images. But there is another interesting part of documents that collects metadata. It's not very huge. It's 2,500 captures. 200.5 captures, sorry. And there is a third type of documents that collects weather observations from a single site in Talarn in the Pyrenees. So this, as you can see, the most of the information is collected as hydrological charts. And we'll have a look now on the storyline of this kind of documents. See here, you can see the format of the documents during the first period from 1922 to 1924. It's curious that it's in English, but this is due that the first companies were from England, so they reported all the information in English. But there is poor information of poor weather information available, only some descriptions about the weather in a single site. But since 1925, more daily meteorological information is provided. The format changes deeply, and from this period up to 1934, we have information about temperature, maximum and minimum, present temperature at 8 o'clock in the morning, precipitation, and interesting, the snow depth in several sites, as you can see here. Barometric pressure as well. And this information during the following years are implemented in several other stations. As you can see here, since 1940s, the available meteorological sites grows up with other stations available. But there is a gap between 1945 and 1948. We don't know exactly what's the reason for that. Maybe there was a change in the company, and that could lead to this gap, but we don't know exactly the reason. And you can see that the hydrological charts indicates and shows meteorological data for several sites. And finally, in 1980s, the meteorological information grows up deeply, includes information about 35 observation sites, and the data is more complete. For example, cloudiness, the type of clouds, visibility, wind force, and direction is provided by these sites. But in mid-1990s, this collection ends, and this is because the automatization of the power plants caused the network to finish, because mostly of them were manned stations, and unfortunately, I think most of the sites stopped the information, and in the later years and at the end of the 90s, thanks to the installation of automatic weather stations, the continuity of these registers could be possible for some sites. As I mentioned later, there is a nice collection of data of snow and ice depth in a single site. It covers the period from 1928 to 1972, and it covers several information on snow depth, ice depth, height, and cubic meters of water from Cabdella lakes that is a specific site above 2,000 meters in the Pyrenees. And I don't know if it's possible to see, but this information is provided weekly or twice a week. And so we have a nice evolution of the snow depth in this site. But unfortunately, by now, the series stops in 1972. We are, as we will see, as you will see later, we are now trying to detect more documents that could lead to a deeper analysis and to expand this period. So as a summary, this is the available information for this collection. In the map, you can see the location of the stations. As you see, there are more stations in the Pyrenees, but other stations were installed outside the Pyrenees because there were I think sub-electrical stations that ruled this information. The evolution of the numbers of stations available is for the first period about 10 stations, but for the 80s this grows up until 35, and in blue these sites are located in the Pyrenees, and in the text you can see the available data or variables that covers all the periods. So mainly it's temperature, precipitation, snow depth, and for the later period more information is available. But which is maybe more interesting. Obviously, the data is interesting, but also metadata, as you know, is very interesting to collect. There is a nice collection of data, of maps, inventories, instruments that is available, and this will help us to improve our knowledge on the metadata. For example, on your left, there is a map with the specific location of the rain gauges in one specific site in the Pyrenees, or in the map on your right there is the information about the specific location of the station and the movement of the stations to another placement. So this will help us to detect these changes. For instrumentation, we have also information about which kind of instruments were used. For example, this is a totalizer rain gauge installed in one station in Stangento, and several Morin rain gauges that were used in the network. So we have a deeper information about the instruments that were used for several sites. And even we have detected also parallel measurements in some sites, comparing the amount of precipitation collected by totalizers and by Morin totalizers and daily totalizers. And there is a comparison of the amount of precipitation for several periods, and this is information this is not a specific parallel measurement experiment, but it's nice to see that the people from these sites were sensitive to that, and maybe it is possible to detect some information that will be useful for the future. And also, as metadata information, we have inventory of instruments installed in several weather stations. As you can see here in the 80s, there is a nice plot showing the available instruments in each site that will help us a lot. So to sum up, this project is for us very positive, because the unknown documentary collection is now available and contains weather and hydrological data. I haven't said nothing about hydrological data, but there is a lot of information about stream flows, about the reservoirs levels that will be useful for hydrologists. Now we are in contact with the authorities that rule these networks, because maybe this information is useful for them. And obviously this collection is now being rescued and preserved and cataloged. As you can see and detected, that metadata has very useful information, and we have now more information about location and instrumentation. And the potentialities of this documentary material is that now a new data set of snow ice is available from one side, and with the information from temperature and precipitation, it will be possible to fill some gaps that are already identified in climate series that are provided by EUMET, by the Spanish agency of meteorology, that will improve the coverage of data. And now this material will be published at the Endesa Foundation digital portal and in another digital portal that is called Digital Memory of Catalonia. So it will be publicly available. And as I mentioned later, more weather data is coming, because we have recently detected other books that contains information on weather data. And this map is it shows the location in 1988 of the stations. So we have information that more stations were are available in some place in the archive, but now the next step is to detect this data and obviously repeat the process that we have already done. And that's all for me. Thank you very much for your attention.
Well, thank you very much, Mark, for this interesting talk. We have some time for questions, if there are. I can't see raised hands.
Everything is clear.
Yes, everything is clear, I guess. Or now we have a break, so maybe everybody needs a short break. Mm-hmm. So we can discuss things during discussion. And so we have a break until 13 Thin time or noon Central European time. And then we have 2 posters. So see you in 15 minutes.
Dubravka, I think the break is until 13:10.
13:10?
Yes.
I have it till 13 in my schedule, but
it has changed. But we can reconvene.
Okay. Well, 13:10 is also fine for me.
13:10, yes.
13:10.
This latest version of the.
Okay, I printed the old version. Okay, thank you very much. And thanks to all the speakers again. The first session, poster session, the first poster will be presented by Martin Santer about data rescue and digitization process in Met Office.
Dubravka, this has been cancelled. I'm sorry. Hardly, you don't have the most recent version of the.
Really? Okay, then Romani.
Yes.
No, I haven't got the most recent version of.
Yeah. Okay. Perfect. Can you hear me?
Yes. Okay.
Okay. I will share my screen.
Yeah. That's why.
Can you see my screen?
Yes.
Okay. Yeah. So, hello everyone. First, thank you for being here. I will not be long. Initially, it should be a poster, but as you know, it's a little difficult to present a poster in this condition. So instead, it will be a short presentation with slides. I will present to you during 10-minute test project that will be launched by RMI in a few months, and we hope that it will work as expected. The project is about digitizing observation of precipitation and temperature extreme from the meteorological reports of the Royal Meteorological Institute of Belgium by volunteer citizen scientists. So first, as you can assume, our RMI has a large amount of climatological data in the archive, in fact more than a century of it. For a few decades, some of the data records have been automatically digitized in our Oracle database, but a large number of old archives are not completely digitized. Moreover, a lot of template forms have been used over time, and sometimes different templates have been used for the same type of information. But as you can expect it, we have some problems. The first one is that in our institute, we don't have a lot of people to encode our data archive. We just have 1 or 2 people and some students during the summer. So this is our first problem, a lack of man or woman power. Secondly, as I already said, we have too many archives to encode. That is problem number 2, too much workload. Due to those 2 problems, we were looking for a new way to do it and try to externalize it. This is when we discovered the Zooniverse platform, and we think it could be a solution to our lack of manpower and workload solution. Maybe some of you already know this web platform. Some data rescue projects have already been made using it. But for those who haven't heard about it, I will explain briefly. Zooniverse is a web platform for people-powered research. This research is made by volunteers. In a few words, it is asking regular people to help us identify or encode data for us. As I speak, already more than 620 million of classifications have been made by more than 2 million volunteers. Zooniverse allows users to classify documents, in our case, images, with a set of different tools. This platform can be very effective when the object to classify is not too difficult to understand. But in order to use these tools, we have to know how we want volunteers to classify our archive. For this first project, we have decided to ask volunteers to encode our precipitation and extreme temperatures data for the time period of 1881 to 1900. Is it clear that we need to create this Zooniverse project with the necessity that it will be at any time user-friendly? Everybody with some basic web browser skills should be able to use it. And first, in order to do it, we need to prepare and sort our archive and select for each set the same layout. And based on those sets created, create the most understandable form to fill in. In addition, Zooniverse allows you to incorporate some tutorials and field guides to help at any time the volunteers. As you can see on this slide, there is an example of a workflow we created. A workflow is a series of tasks and assessments that a volunteer is asked to do. This workflow asks volunteers to key metadata on this bulletin. The metadata are the name of the session, the name of server, the month, the year, and the time of the record. Once done, the volunteer can send the form. In order to avoid mistakes, we can ask that each bulletin can be classified more than one time. For this project, we choose to put a redundancy set to 4 or 5. because as you can see, it's sometimes difficult to decipher 19th century writing and writing. And it's very important that we put some help within this platform for each volunteer. This is why field guides and tutorials are very important. Here you can see an example where we use field guides to how can I say this? Where we can see, all volunteers can see each name of the session linked with a specific observer name. There, the volunteers can retrieve information when it is difficult to decipher on each images. The field guides can be accessed anytime. And the tutorials are more specific to a workflow and are useful to explain how to classify information, as you can see on the second images. But it's really more specific on a workflow and on a specific task. And in addition, Zooniverse permits to create websites on different languages. So we can reach a large number of volunteers from everywhere, not just from Belgium. Concerning the data identification and the data export, each image which will be classified as a unique subject ID, and for each subject set we create, we can create multiple workflow which ask volunteers for multiple tasks. So for this project, as there is extreme temperature, precipitation, and metadata on the same images, each task for a specific image will have the same subject ID. This is how it's possible to match all the information easily. At any moment, it's possible to export the data from the classification easily and extract all the information using a specific Python package. And using this package allows us to get all the results of the classification in a nice CSV file ready to use. But maybe the most important goal of this project is to know how to get as many as possible volunteers. How we can attract them? First, we can make a call by the official LMR website or social media, or by more traditional media such as press or TV. A huge advantage is that the Zooniverse platforms already has an enormous amount of volunteers who like to help research. And in return, it's very important to give back something back to them. And knowing that the help was useful, it can be done by giving them the raw data of the classification, or even better, but with some scientific studies. This project will be launched soon. We still have to finalize some details before asking Zooniverse to beta test it. This beta test allows us to be put forward on the Zooniverse website, and so to reach more easily volunteers from there. If everything works as expected, volunteers should start classification before the end of the year. We hope that it will work. Is that so? We will analyze the collected data from classification and hope for not too many mistakes from volunteers. We will at least publish the result and add value to them and see how we can give it back to all volunteers. And in the future, it will be interesting to see how far we can go with this platform. and see up to which level of complexity a form can be classified by volunteer. Because we have a lot, we have much more complex methodological reports which will be classified. And yeah, that's it for today. Thanks for listening, and I value that we have more news for you in the following meeting. So, if you have questions.
Well, thank you very much for this presentation of your paper. And if there are questions, go ahead. No, I can't see any, but I'm interested if you plan to have a few or at least 2 volunteers entering the same sheet just to get a better result, or if somebody enters blocked.
I don't really understand you because there's some.
Yes, there is a. Yes, there is a background noise in my house. There are some work, so I can't really do much about that. My question was if when volunteers enter the data on one sheet, do you plan to leave it for other volunteers to enter the same data, so to have double?
Yeah, we decided to put some redundancy, and each images will be classified at least 4 times in order to try to avoid mistake. And so we will compare all the 4 classification and see if 3 of them have the same encode data. We will take this one and not the fourth one. I don't know if it's answer your question.
Okay. Yeah. Thank you. Okay, Mark.
Yeah, it's just a comment on your presentation. It's very nice, and I think that it's a good point to attract people to digitize this data. We have a small project here in Catalonia, and the more sensitive volunteers are those involved in meteorological societies, amateur meteorological societies. So maybe this is a good point to go for and to attract people. They are fond on digitized data, and they are very sensitive. So it's just a comment.
Okay, thank you.
You're welcome.
So if there are no more questions, I don't see any. We can move to a discussion part. So we can begin with questions if anybody had questions for Agnieszka, or after her presentation, we didn't have time to pose questions, so you can do it now. So no questions. So if not, are there any proposals for a discussion for data rescue topic from your side? So the main problem is always manpower, I guess, and problems with OCRs. So it takes a lot of time and people to key the data so that we can use it. But if there are no comments, I would like to bring up the topic of what recently happened in Croatia with our meteorological station and data, part of the data archive. after the earthquake in Zagreb in March, 22nd of March 2020, our headquarter building was hardly damaged, and it was we have the most important data logs in that headquarter building, and also our Centennial station Zagreb Grič is located in that building. So we had quite a struggling time, not only COVID, but also this earthquake problems. I can share a screen. I have some photos so that you can see if you're interested in that. And I would like to know if your archives, your data logs are protected from these natural disasters that can happen anytime. So I can just. Is this background noise very strong?
I cannot hear it at all.
Sorry, now I have really to talk to people. Just a second, I'll try to say the workers to stop for a while. Sorry for this distraction. It will be some more noise soon, but I can't do anything. Do you see?
Probably it's okay. It's not annoying. I mean, we don't have this noise.
Okay, not now, but they will
don't worry,
make another hole. Sorry. So this is our building, and some of you were at a data management workshop in 2017 in Zagreb. So you saw the building. This is after the earthquake, and this is the entrance to the meteorological observatory, Zagreb Grič, that got the Centennial station recognition from the WMO. This is how it looked inside, and it was even worse after the second earthquake that we had in Petrinja, that is like around 50 kilometers from Zagreb, that made more damage to our building. This is some also parts of chimneys that fall down. It happened in the morning and it was during the lockdown. So fortunately, there were not really many people in the building. It was also Sunday, so there were just forecasters and observers. This is the corridor. It's a quite old building from 19th century. And it was not in a very good condition even before the earthquake. And that morning it was snowing. It was very nice weather days before that day. And then it started to snow, what made the situation even worse. This is the roof, where chimney fall on the roof and destroyed it. On this window here, we have measurements, and as it was too dangerous to enter the room, we had to stop manual measuring. And we have homogeneous data set from 1862 from the same site. It's really homogeneous because It just moved from one to another window, but it was always here at the same place, and it's in the upper town where we don't really have construction works anymore, no new buildings, and not so high influence of urbanization, or at least not a direct influence. But fortunately, we had automatic weather station at the same window, so the sensor kept working. So we still had data from that window, from the same spot. So this is the roof from above. So now you can see that how damaged it was. This is my office. So if I was sitting there, I would get this part of the ceiling on my head. And this is how it looks now. Actually, the building is now, the government gave the building to the Croatian Historical Museum, and they will repair the building. So we had to take our data logs from the building, and it was not possible from inside to pass through the corridors that looked like this. So we had to arrange the crane and the track and to get it out from windows. So this is from inside the materials that we prepared. So this is where the oldest data logs are or were stored, not anymore. And this is how we did it, because in the building there were only our employees, because it's too dangerous still to get some students or anybody else, some workers, to do that. So people enter on their own risk. And this is how we took the materials to the track. And this is, I would say, everything that we could save. There are some data from projects that lasted some measurements from several years. So we left that materials inside because it was in other rooms that were not acceptable. So we couldn't really organize to get everything out. This is the station, the sensor of automatic station for temperature and humidity, and inside we still have air pressure. This is the garden with precipitation measurements. We moved that a little bit further from the spot where it was, so to lower the danger for observers, because something can fall still from the building. So that's it. And now I would like to know how your materials in your countries are stored. Is it a problem if something like flood or fire or earthquake happens, or are they protected professionally? Yes, Isaac.
Hi, Dubrovka. Wow, what pictures. It looks really, really wow. Regarding the Israeli Meteorological Service, I have to admit that this was the case until last year, I think. We needed to make some reconstructions in our building. So we needed to remove all our archives from the building of the Met Service. So we took almost all the employees that we've got in order to pack all these things according to their priority. And some of them we kept in another storage that is next to our building or inside our building in the shelter, by the way. And most of the materials moved to an archive, which is specialized in archiving. You know that this kind of materials need a specific humidity, specific temperature in order to maintain them properly. But the problem is that if we are interested now in a paper, in an historical one, we need sometimes to wait a couple of days until we are getting this paper. But all this data rescue is a huge project, and unfortunately in Israel, it is going quite slowly from all the reasons that all the speakers have spoke about them. And here in the previous talk, I saw mainly scanning of books, but we know that we have some, I'm not sure I know the right expression, a wind chart, like a film, when a needle is writing all the records. How you are scanning this kind of material? We have them for precipitation. You can actually calculate the precipitation intensity, or wind. You can look for wind gust and the average wind and so on. And this is another kind of scanning, which I think that that there are no much skills and developed software regarding this one. If someone familiar with this kind of techniques of scanning, I'll be more than happy to hear. So thank you very much, Dubrovka.
Yes, we have some tools for digitizing precipitation data from those kind of sheets. This, as you explained, so I can get some details and send you if you are interested in that. Yes, and like
be great. Thank you very much.
Yeah. Okay, you're welcome. We kept that data logs in our building because, as you said, you need a few days to get data logs if they are stored somewhere else. So that's materials that we need not daily, but quite often, and it's the best to have it close to you and to have easy approach to that. And as we are for like the last 20 or more than 20 years waiting for our new building of headquarters to be built, where we plan to have a proper storage place for with conditions, proposed conditions of humidity and temperature and so on, but we still don't have that building. We have a project ready, but no money to build a building. So that's our problem. So anyone else?
Hello. I cannot see the hand to raise hand in my Linux application of BlueJeans.
Okay,
sorry.
just go ahead.
There are several softwares available, well, more or less available for, or at least developed for digitization of strip charts, but some of them need you to point with the mouse on the significant points of the graph. Others, for example, the AIDRO Foundation for Data Rescue have something about that. I know there are at least a couple more initiatives. I'm glad to hear that Croatia has his own software. And also Federico Soto, which is a scientific officer of WMO office in Costa Rica, had initiated a program that detects the line automatically. But he's very busy and didn't finish it. And the step that he needs to finish is once you have the line detected, to convert it to numbers, to do the real digitization. And on there is a project on several Andean countries in Colombia, Peru, and Chile, which is called Hernandez and supported by WMO and the World Bank. And in the frame of this project, I suggested to join efforts in order to produce a standard software for this work, because another guy in Chile, they said that they had also some advanced student in a university had produced another software for this. And I said, well, we are doing parallel work on this, and it would be good to unify these efforts and to produce something in open software that would be very valuable for the Open CDMS project also. But it's difficult to put people in cooperation in such diverse entities and institutions.
So, Jose, as far as you know, this should be still done manually by an expert with a mouse. It doesn't matter. So all this digitization of this stripe of chart stripes should be done manually by an expert?
Well, not need to be very expert, just to identify the graph in the chart in the scanning. But yes, at least I saw the Ayedro. I think they have this tool they have open in their web page, and I tried to run it, and I don't know if I had problems because it was a Windows application and I'm a Linux user. But anyway, I read the manual, and yes, you had to define because sometimes the strip chart is not perfectly horizontally scanned, so
there is
you
a
must
deviation,
define the baseline, and then some coordinates in order for the software to be able to put numbers or to measure the magnitude. And then you must click on the significant points, changing points in the strip, in the graph. So it's something that takes time. Yeah, it's not perfectly automatic.
Okay, thank you.
Yes, that's the same what we do with this precipitation strip charts. It's also, we have a special mouse that is connected with the computer and with that program, that also the person doesn't really need to be an expert, but a technician who needs to click on the corners and some significant points. That's how it reads the data. Yes. But it's not something very complicated. Anybody can do that. But it is time consuming, but much faster than, I don't know, reading and writing the data from it, and more accurate. So anybody else with experiences with scanning on data rescuing or some other topic on that? So if not, I guess we can conclude this session. Janusz, do you agree? Or
if there are no other comments or questions or whatever, Dubravka, I was really sorry to see the situation of your building. I was among the bad, but well, I hope that you'll be able to repair the damage as
alive,
possible.
the most important for us now, that we all survived that.
Yeah, this is the.
Yes.
I would like to thank you very much for accepting to chair the session of this day. So we will well, actually, session starts in 4 now. Ready to chair the next session. So we will. So we can resume our workshop. Now it's time for session number 4, quality control. The German is from the service. I apologize if the title is not accurate. So the floor is yours.
Thank you very much, Thanos. So I'm very happy to open the quality control session. It is well known that quality control is the most fundamental procedure before conducting any research or getting into a conclusion. Of course, that it's not just in climate, it is in many other fields as well. So in our session, we've got 3 lectures in total. 2 of them will be right now and 1 more after the breaks. So I'm delighted to invite our first speaker, Vincent Change from Environment and Climate Change Canada. He will present a quality control system for historical in situ precipitation data. So Vincent, please, the floor is yours.
Thank you. Can you see my screen?
Yes.
Great. Thanks. So today I'm going to talk about the quality control system for historical in situ precipitation data. This is ongoing work with colleagues Xiaolan Wang and Yan Fan in the Climate Research Division in Environment and Climate Change Canada. This work is part of our ongoing effort to develop an in situ homogenized precipitation dataset for analyzing long-term trends. So in situ precipitation data are recorded at observing stations, typically using either manual or automated gauges. Unfortunately, there are random erroneous values, which could be unusually large values or false zeros. The latter usually arose from misrecorded missing values that are missing values were misrecorded as 0 precipitation in the climate archive. Now, most suspect outliers have 0 monthly total precipitation. In the past, we tracked surrounding stations of data for those times to decide if a suspect outlier is really an erroneous value or a real extreme value. So in Xiaolan Wang's 2017 study, we screen out long runs that is longer than or equal to 3 consecutive months of miscoded missing values in the adjusted daily rain and snow dataset, which did not screen out shorter runs that is less than 3 consecutive months of miscoded missing values. So here we present a new quality control system for the Canadian in situ monthly precipitation data records to identify 2 types of random errors. First is the outliers of unusually large values, and second, the outliers of 0 or near 0 monthly total precipitation. So we have applied a new QC system to 2 datasets. The first dataset is the updated version of the adjusted daily rainfall and snowfall dataset. There are 3,346 stations in this dataset for which we have metadata to do the adjustments. There are no joining or homogenization applied to this dataset. And the main use of this dataset is to produce gridded precipitation datasets. We QC the monthly precipitation calculated from this daily dataset. The second dataset we applied is a joint 46 data series. It is a core network of station joint series to form a long record to undergo homogenization testing for the purpose of analyzing long-term climatic trends and variations in Canada. The core network of precipitation stations are chosen based on analysis of precipitation data records for all active automated stations in order to identify active automated stations that will be sustained in the future. So onto our QC system. There are two procedures. In both procedures, we first deseasonalize the input data series by calculating the long-term mean for each calendar month and then subtracting the long-term mean annual cycle from the data series. Then we estimated the trend line, that is the mean, and the standard deviation of the deseasonalized series. We used the Mankando method to estimate the trend line of the untransformed series because of the non-normality, and we used the least square estimator to estimate the trend line of the log transformed series, which is approximately normal. Then we screen out all outliers that deviate more than 6 standard deviation from the mean, that is the trend line. Note that we try to use 3, 5, 6, 7, and 8 standard deviation as a threshold to screen out suspect outliers for investigation, and we found that 6 standard deviation is the most appropriate threshold to use. Thus, we screen out all monthly values that deviate more than 6 standard deviation from the mean as suspect outliers. And then for each suspect outlier, we compare its deviation from the mean seasonal cycle from the counterpart at 4 nearby stations within the 200-kilometer radius. After visual inspection of all the data series of one or more suspect outliers, we have concluded that the threshold described below are reasonable ones to use to set the suspect outlier to missing. So for the suspect outliers of larger values, which are detected from the untransformed series, if the magnitude of the suspect deviation value is at least 2 times as large as the largest counterpart at the nearby stations. Many outliers have deviations to the opposite side, actually. But the suspect would be deemed an outlier and set to missing. We also set the suspect value to missing if the suspect value at least A has standard deviation at least of 7.3 above the mean, and its deviation from the mean is at least B equal to 1.6 times as large as the counterpart at the nearby stations. While A plus B has to be at least equal to or greater than 9. We use visualization of the data series to help determine if the suspect is an outlier or a real extreme value when there are no nearby stations within the 200-kilometer radius. Just so to summarize this as the formula here, B has to be greater than 2.0 or A has to be greater than or equal to at least 7.3 and B equal or greater than 1.6 and A plus B has to be greater than 9.0. Now for the suspect outliers of 0 or near 0 monthly precip values, if the minimum of the absolute difference between the 4 nearby stations is at least 10 millimeter or greater, the suspect outlier is then deemed an outlier and set to missing. Note that all the outliers of monthly precip of 0.36 millimeter resulted from miscode, the missing values. The small non-zero monthly precip values are a result of trace precipitation adjustments, while the original values are all zeros. So here I'm showing the 2 examples for the adjusted daily rainfall dataset. Well, first we identify 173 erroneous outliers, within which 74 are 0 to near zeros, and 99 are unusually large values from 150 stations. So the first example is an outlier, as a large outlier identified from the untransformed series, which occurred in 1934, if you can see my cursor, at the Chinook Cove station in southwestern Canada. in the British Columbia province. So first of all, the outlier has a standard deviation of 8.9, so it is screened. And then upon inspecting from the nearby neighbors, as shown in the map, the deseasonalized values of that station has a value of 198.6 millimeter, and which is greater than, or at least 2 times greater than the largest neighbors for that month, which is 5.7 millimeter at this station. So it is deemed as an outlier. Here on the right is an example of a false zero outlier. This zero value occurred in the Thunder Bay airport in 2003 of July, so which is here in the time series. It is screened out because it has a standard deviation of 7.3. And then upon comparing with 4 nearby stations, so all of them have values are at least 10 millimeter or greater. In this case, at least 98 millimeter. So because it fits that criteria of 10 millimeter or more, so this is also deemed an outlier. Oops, excuse me. So for the joint 426 dataset, we identified 28 erroneous outliers with 4 cases of with 4 cases of low outliers, and 21 of which are false zeros resulted from miscoding. And we have 2 unusually large values in total from 17 stations. So here on the figure on the left shows procedure 1. The 2 outliers here are screened out based on the standard deviation from the untransformed time series. But there are also outliers of 0 monthly precipitation that are not detectable in the untransformed series. Now for the same station, which is shown on the right, but in a log transform series, several outliers of near 0 monthly precip are correctly screened out, as shown here from this log transformation. But the large values were not able to be screened out initially here. So the key message is that we found that in order to identify both types of outliers, one must screen both the untransformed and the transformed series. So in conclusion, we developed a quality control system to identify 2 types of random errors, unusually large values and false zeros, for historical in situ monthly precipitation data. We applied it to 2 value-added climate data sets. The first is the monthly values of the adjusted daily rain and snow data set, and the other is the long-term monthly precipitation data set that included joint and homogenized data series. And we will apply this QC methodology to a few more data sets in the future. Thank you for listening.
Thank you very much, Vincent. We've got time for a few questions. So if there are any questions, please push the raise hand button. Well, I don't see anyone. So, Vincent, I would like to ask if this program can be applied into the daily rainfall. You mentioned the homogenization. I think you probably implemented the daily precipitation homogenization methods that developed by Xiaolin Wang. And so before you are actually doing homogenization, first you should do a thorough quality control for your daily precipitation. And I'm wondering if your program that you spoke about, monthly averages, can be transferred into daily as well?
First of all, we applied it to monthly values. We did not apply it to daily. But so if we were to apply it to daily, we would likely have to change the threshold values a little bit. These are values set for monthly. But when we QC for these monthly values, we also inspect the daily values. However, this methodology is applied to monthly. We have not applied it to daily.
Okay. Thank you. Any other question for Vincent? Okay. So I think we will move to our second speaker for this session. Our second speaker is Colm Stone from UK Met Office. His talk will be on a new quality control system for marine observation at the Met Office. So please, Colm, the floor is yours.
Thank you very much. Hello, everyone. It's my first time doing a presentation across Zoom, so hopefully the technology will hold up. Can everyone see this? Is this okay?
Yes, yes, yes.
Okay, thank you very much. Yes, so yes, hello. My name's Callum. I'm a marine data specialist, and I run the UK's Global Data Assembly Centre for voluntary observing ship observations. Yeah, we're going to talk about some new developments that we've had with regards to the software that we're using to do quality control on various aspects of our marine observations. So the Met Office gets data in from a large variety of marine sources, but we're going to focus on three types today. These are our moored platforms, of which we've got about 15 around the UK, our automatic ships, which are completely autonomous, self-contained units on ships around the UK, and some go further overseas. And also we've got about 300 voluntary observing ships, which have meteorology equipment supplied by the Met Office, but the observations are done manually by volunteers on the ships. And these all undergo various forms of automatic, but then also manual or expert quality control. And these systems are continually changing and being upgraded, so the tools that we use to apply quality control need to evolve to maintain the quality. So a rough idea of what we've got around the UK. These are not all the automatic ships. There are some, but for the purposes of what we're talking about, these are roughly sort of 80%, I think, of the automatic ships, and our moored platforms. So the most important directions for the UK, a lot of our weather comes from the west southwest area. So you can see we're trying to cover that area as much as possible. We do have observations out to the east in the form of observations we get from oil rigs, but they undergo a different process. And this is a map that was included in the latest Global Data Assembly Centre report generated by ourselves and DWD. And this is showing the range of voluntary observing ship observations that we've received from not just the UK, but all the contributing members around the world in 2020. And again, just to sort of emphasize the importance of getting the quality control as good as possible. A lot of these places, particularly in and around Antarctica and the South Pacific, South Atlantic, there's very little other ground truth apart from these voluntary observing ship observations. So ensuring that we can get the maximum value out of those is one of our priorities. So for data flow into our databases, they undergo several steps. For our moored platforms and automatic ships, we have the data being sent through satellite relay in the ship code that undergoes some initial processing, which performs automatic quality control checks to remove things like corrupted data, and also it does a few range checks. For example, it will remove if there's a buoy, for example, is reporting a pressure of less than 870 hectopascals, the system decides that that is pretty much impossible, and it will remove that automatically. And then it is ingested into our main database, and it undergoes approximately 400 unique checks applied automatically. And these are for things like step changes, for range checks, climatology, and also for things, for example, if it's trying to say that it's got a dew point without an air temperature, things that are impossible there. And then it's ingested into the database, and then it's then manually checked by eye by the observation quality management team, of which I'm a member, and we go through the data and make sure that it's all within reason, producing good data. So the automatic quality control checks, some of them it will apply a finished check, and some of them it will apply a sort of temporary check, which then it highlights for us to go over manually. For the voluntary observing ships, they send data in real time, which goes through only the automatic checks, and then we get the data in delayed mode, where it is supplied by our port met officers, and then undergoes similar checks, except they're slightly more targeted, just due to the volume of data and the time and resource constraints. But they undergo further quality control checks when they are shared through the GDACs. So we use some bespoke tools that have been recently created by our in-house software teams to achieve the quality control aims. The main tool is MIDS, but we also use ones such as Drifty and Marlog, which I'll explain as we go along. The screenshot there is a screenshot from Marlog, and basically that is a tool for extracting metadata from large files in the IMMT format, which is the delayed mode format from the voluntary observing ships. And this will do things like present metadata for amount of observations per vessel, and also if there are duplicate observations, things like that, it'll pick that up as well. And the main tool that when we're going through the expert or manual quality control phase, we use the eSurfMar O-B checker as the main tool. So MIDS is our primary tool for interacting with the data in the database, and it's been designed specifically to make manual quality control as easy as possible by trying to be intuitive and making sure that the errors stand out. As you can imagine, when you're spending a lot of time looking at large spreadsheets, it can become easy to miss things if they don't stand out. All the numbers will start to blur together. So the program displays the data, but it also displays the quality control flags that we can apply in the same location. And it also includes useful metadata, such as the date and time of the observation, but also the location of it as well. So you can see in the picture there, it's highlighted 2 rows in the light green, where it thinks that there's been a change that needs to be looked at by human eyes to verify. MIDS can also adjust the number of columns of variables to suit different observing networks. So our automatic ship network only supplies temperature, humidity, and pressure, so you don't need too many columns for this, whereas the voluntary observing ships supply many more. I don't expect you to be able to read the text there, but if you note the size of the scroll bar at the bottom, this page goes quite a long way off to the right to account for all the different variables that can be observed by the voluntary ships. One of the main advantages of MIDS over other ways of looking at the data, like just data tables in SQL, is that we can get a visualization of where the ships are. So on the left, we've got a ship that was performing some work around one of our moored buoys, and the one on the right is a cargo vessel of the voluntary observing fleet, which has been transiting around the world. And this is very useful for picking up errors where if the latitude or longitude has been recorded incorrectly, it will stand out exceptionally well on these tracks, and then we can try and rescue the data if possible, or if it's impossible to put into a reasonable location, then we will remove it to remove errors from the data set. So it's also very good for picking up when ships are incorrectly reporting that they are on land, or if our quality control checks think that a ship is on land. For example, if it's in something like the Kiel Canal or in the Norwegian fjords, it's not got enough resolution, but we can look at this map and see that actually the data is okay. It also contains a link to a vessel finder where ships are reporting their position through AIS. And this allows us to find the particular ship that we're looking at and see where it is in real time. And this is useful, for example, if the ship has gone into dry dock, where the readings may become corrupted due to maintenance work or other factors happening near the sensors. And we can then remove those sensors from the general circulation until the ship is left. It also includes a basic O-B statistics page where it looks at the root mean square error against the Met Office's unified model, and it will show sensor drift in a good way. The resolution on this one is on a monthly basis, but we'll talk about Drifty in a second, which goes into much more detail. So yes, Drifty. This is a tool that we've developed to detect sensor drift within marine observations by looking at how they compare to background model. It does short and long term biases and root mean square errors, and it does it between the Met Office's global model, but in and around the waters of the United Kingdom, it uses our 1.5 kilometer resolution UKV model. And it will do this over a variety of parameters, such as air temperature and pressure, etc. And it will calculate the difference between hourly observations and the background model. It'll then create a daily bias and root mean square error, and also calculate those two over longer term as well. And it highlights occasions where the moving average is greater than one standard deviation from long-term values, so we can start to see if sensors are drifting, or if sensors are not performing particularly well. And the average period can be adjusted, as well as a synoptic filter, which has been added as well, to remove short-term noise. And we'll get onto an example of that in a minute. So this is an example where we've got an averaging period of 5 days, and the synoptic filter is getting rid of errors that take place over less than 2 days. And this is an example of where a sensor has been fitted to one of our automatic ships, and it's not performing particularly well. In the data, this sometimes doesn't look like it's too bad, but over time, and you can see particularly on the bottom graph, it's pulling up a lot of errors for the root mean square against the model. And so sometimes when the differences can be almost too subtle to see on a day-to-day basis, this program is extremely good at picking out where the longer term trends are not so good. And this allows us to send out our engineers to go and replace the sensor. And in the meantime, we can turn the sensor off to reduce the impact of the low quality observations getting into our models. And we can zoom in on particular periods and adjust the moving average to try and catch longer term drift as opposed to shorter term errors. And the synoptic filter, as I mentioned before, is good for reducing the noise generated by model inaccuracy, which is one of the main things that we're trying to sort of fight against here, where the models don't get everything right all the time. So the risk when you're using them as a primary quality control method is that you will be not accounting for model bias when using it. So you may end up thinking that a sensor is not doing particularly well, when in fact the model has been performing poorly in a particular area. So the synoptic filter helps to catch out those areas there. So you can see it's picking up quite a lot of errors on the right-hand side. Particularly, we'll look at one example on the 23rd of February this year. But then if we extend the synoptic filter to cover 5 days, it no longer is highlighting this as an error because it's reduced the sort of sensitivity to noise. And so this was a a buoy of ours, buoy K7, which is out to the north of the UK. And around the 23rd of February, there was a lot of fast-moving pressure systems, which the models hadn't quite captured successfully. And so it was trying to say that there was a good deal of deviation in the O-B, but thankfully we were able to sort of filter that out and determine that the buoy is reporting accurately, and it's in fact the models that were not doing very well. So yeah, to summarize, we've continued to develop our QC tools to adapt to new ways of working and our evolving observations networks. We are in fact extremely fortunate with the timing of this. We had previously used a system which had to be physically installed on desktop computers. We switched to this in, I think, January 2020, before we were all asked to work from home. So we were able to install this on multiple laptops and take them away rather than relying on our previous and fairly old system. The design focus has been heavily towards increasing usability and decreasing the time needed to perform QC tasks by highlighting and making it easy or easier to determine when there are errors which need to be excluded or sensors that need to be suppressed. And because these have been built in-house using pretty much off-the-shelf programs, most of this was done in Python and SQL, we can adapt these tools with relative ease as we continue to upgrade our observing systems. And any questions?
Thank you very much, Colm, for an interesting talk. And now, are there any questions? Can you please stop the sharing, Colm, so we can see all the. Thank you. Yes, Thanos, please.
Thank you, Itik. Thank you, Colm, for your very interesting presentation. I would like to ask, are there any that can be distributed describing the algorithms you use for the quality control tests?
Sorry, I think you broke up slightly when you were talking there. Could you repeat the question, please?
Yeah, the question is, are there any reports that can be describing the algorithms you the control of the various parameters?
Thanos, we can't hear you clear.
It's yeah, you can pass to someone else. I'll write the question down. And
okay. So, is there anyone would like to ask, to comment? I would like to ask if the VOS, the volunteerships and the automatic one, transmitting the data online on a real time, or just when they are coming back to the UK, you are download the data and doing all the procedure?
So they do both. They transmit in real time, but the data doesn't contain, or the message doesn't contain all of the data that's available, I believe for a sort of cost saving measure when they're transmitting. So they transmit this sort of basic amount in real time. And then when the ships come to a port where we've got one of our port met offices, they can ask for the ship to send the full data in this IMMD format through a program called TurboWin. And that contains a lot more, it's mostly metadata that it contains that helps describe more about, for example, the ship will report wind, but it doesn't necessarily report, the speed of the ship, etc. So you can't sort of take that into account, but you can when you have this extra data.
Okay, and what is the time resolution of this data?
So the time resolution, it is done every hour. Although with the volunteer observing ships, we are very much dependent on the availability of somebody on board the vessel to do the observations. So if they're extremely busy, for example, we might not get data for several days, but we try and, when we're recruiting the ships, we try and emphasize that basically the more data they can give us, the better we can then make the forecasts and the data sets that we've got.
Mm-hmm. And by the way, who is in charge for the maintenance, the calibration for the equipment that are on the vessels?
So we have a calibration lab in the Met Office. A lot of it is on the sort of the purview of the port Met officers. They will try and visit these ships as much as possible, and then when data needs, when the sensors need to be calibrated, they will try and replace them within the calibration date. A lot of these instruments are quite simple as well, liquid in glass thermometers, aneroid barometers and these sort of things, and some of them are using the ship's own sensors. For example, for sea surface temperature, they'll often have a sensor in the engine water intake inlet where they can get this data from.
Great, thank you very much, Thanos.
So I can see what you've written there, Thanos. I honestly, I'm not sure on that one. I will have a look and see if I can find it for you and send it across to the email that you've just put there.
No, we can't hear you, Thanos. But okay, any further questions, comments? Okay, so I think that we'll have a break now. We will be back at 3 o'clock Athens time in about 35 minutes from now. So see you at 3 o'clock. Thank you very much for your attention and for the speakers. Thanks. Our last but not least speaker, Peter Stepanek from Global Change Research Institute in the Czech Republic. He will talk on data quality control and homogenization of various meteorological elements in the Czech Republic for purpose of a new climatological normal. So please, Peter, the floor is yours.
Thank you, Itzik. So yeah, I have to start sharing the screen. Yeah, so hopefully it works.
Yeah.
So I will speak about data quality control, but also about homogenization, our experiences from the Czech Republic. This contribution was developed by several colleagues, not only from Czech Globe, as we call Global Change Research Institution, but also Czech Hydrometeorological Institute. The motivation for this work was processing of the new climate normal. And with this, we processed also the older climate normal. So we processed the period from 1961. And to be able to prepare new climate normals, so we need to devote to data quality control, to homogenize the time series, and also fill missing values. And at the end, to select the stations that will be suitable for purpose of the climate normal. The mentioned processes were improved within this work, mainly in the field of data quality control, and it was achieved in cooperation with KNMI. Here is map of the Czech Republic, but I think that the points are very small, but it shows generally several hundred of stations that were processed. So as for data quality control, in this part, I will devote rather to methodology, what is new, update some older results. And when I move to homogenization, I will show some concrete examples on two methodological elements. So let's start with data quality control. So here you can see flow of the processes. We start with selecting neighbors. For comparison detection itself, what we focus or what we do during our quality control, we emphasize also outputs that help users to go through automatically detected problems. So we create various tables, graphs, also maps. And in the end, we flag the results. We also calculate within the process what we call expected value. And the results are then quality control data. As for the process itself, so when we start with selection of neighbors, we work with correlation coefficient, distances, differences in altitude, and also with common period between candidate and reference series. To be more concrete, we use from 6 to 8, or sometimes in case of precipitation, even 10 neighbor stations. We work with either 10 or 20 years long periods because number of station changes between the periods. And the selection of neighbors is done automatically, but still it is the same also for the other parts of the process. User has always full control about the process. You can check what was automatically suggested and change it if you would like, in cases of, for instance, mountain stations, if you would not like the selection. This is example of such table with selected neighbors. The selected neighbors are in the second column, and you have information about correlation, distances, and altitudes, and other stuff. The quality control itself is based on several statistical tests, and we can divide them into two big groups, either based on time evolution, for instance, interquartile ranges, and on spatial analysis, when we compare neighbor of candidate station with its neighbors. And the point is that only combination of several tests leads to satisfying results when we run it automatically. So what I mean is that individual statistical tests are okay, but if you want to automatize it, it's needed to combine them all together. Special thing in the process is what we call estimation of expected value. It is calculated from neighbors without knowledge of the candidate value. And it serves then either for comparison what is expected at the place, but in case you have missing data, we use this approach also for filling gaps in time series. And here are some results from validation in case of temperature, daily temperature. The correlation coefficient is almost 1 between estimated and real value. In case of daily precipitation, it's a little bit worse, but still coefficient of determination is above 0.8, so it's still very good. So the outputs of the quality control process are tables with errors, but also tables with only suspicious values. We also detect repeating values. Sometimes you have, for instance, repeating values, and also duplicated values. It means the same values with neighbor stations. It may be some errors during digitization and so on. Here is example of graphical outputs where on the first plot there are standardized values. On the right and top, standardized differences. Then first differences, and some statistics. Here is an example of a map generated for some found suspicious values, where you can see the value in the context of neighboring stations. As for the flags, so we flag the values in this way: 0 for no problems, 1 means erroneous value. We also estimate probability of each detected value. So here is the range of probability. Then suspected value. it continues with repeated value when you have the same values in the given time series. Duplicated values, it means same values with neighbors, and we like also missing values just for some statistical purposes. So if I should conclude this quality control, how we enhanced it. So we create tables with suspicious values which are ordered according to their relevance based on estimated probability of an error. We also generate maps which are of really big help. You can easily check what happens in the space. And to the outputs, we also we put it into a context with other meteorological elements. For instance, various temperatures, precipitation, sunshine duration. So because if you have some strange change in one element, so it's also handy to have a look onto the other elements, what happens in them. And all of this is running operationally in daily step. Newly we put it also into hourly step, and it works quite well. The last slide, pertinent to this first part, only one slide about interpolation, because I mentioned it. So the interpolation that we use, it is based on regression kriging with dependence on predictors coming from various terrain characteristics like altitude, wind slope, exposition, and so on. So now I will move to the second part of my presentation. It will be about homogenization, and I will focus on two meteorological elements, wind speed and precipitation. So only very briefly, what is the methodology? We run detection on monthly, seasonal, and annual time series. We use two types of reference series, either a reference series calculated as a weighted average from several neighbors, or in pairwise comparison. And we still run this older statistical tests, but they work, so we still use them. As for correction of inhomogeneities, we correct data in daily scale. And for that, we use our own method, which is based on quantile mapping. And we use it also for bias correction in case of regional climate models. So the methodology is very similar. And generally, what can be thought about is that for different quantiles, you can have different corrections. So in this way, you can also correct variance or higher statistical moments. So now I will speak about some results of wind speed. So first of all, meteorological instruments that we use for it. In the upper part, you can see old Metra anemograph, which was used before automatization. On the bottom left, there is a Vaisala anemometer, and in the last years, it started to be replaced with ultrasonic anemometers. What is important in case of wind speed, it's calibration. Because without calibration, you get lower and lower wind speeds and higher numbers of columns. What is important in case of wind speed is also surrounding of the station. Here is example of one station where continuously in last decades forest started to be developed. So in the end, the station is surrounded by forest, which was not the case in the past. So now the results. we present here not the wind speed or wind gust itself, but number of days with wind speed above a certain limit, because we use this also to help us with detection of breaks. On the left side, you see various limits. And what is important is that in all the cases, almost 100% of wind speed time series are inhomogeneous. And there are usually from 2 to 3 breaks within the last 60 years period. What is interesting that for lower wind speeds, the cause of inhomogeneities was mainly caused by relocation of the stations, while for higher wind speeds, the cause is automatization. In this slide, you can see it in a different form. So in case of low wind speed, in this middle left graph, you can see that the cost of automatization is quite high. And the same is valid also for high wind speed on this right column plots. And you can also see that there are two big peaks. One of them is caused by automatization when we changed to Vaisala anemometer, and the second when we changed to ultrasonic anemometer. Some examples of the station. So here, top and left, in the blue, you can see raw data, and in red, homogenized data. So the cause was automatization, then another inhomogeneity was found after calibration. Here in the middle and left, cause of automatization. On the bottom, relocation, and again relocation. In case of Protimanov, we have no metadata, and you can see several breaks. In case of Červená, it was seen on the picture, some slides before this. So the cause was afforestation. So we corrected the decreasing trend. And the last example is Česká Lípová. The cause was relocation in the beginning of the series. What is important to realize is that the trends change quite much in raw and homogenized data. Generally, there is wind steering, but it has probably natural cause. But after homogenization, the found decreasing trends are a little bit lower than in raw series. So here are a few examples. And the examples here are on the bottom are for the whole Czech Republic, while on these pictures it's for various altitudes. So you can see it's in every altitude we can see the same decreasing trends that are then a little bit lower after homogenization. When we compared the last two climate normals, so it means period from 1961 to 1990, and the new one from 1991 to 2020, we can see big differences in case of wind speed. Here it's in form of time series on the left column. So there was rather increasing trend, but in the last normal we can see very big decreasing trend in wind speeds. In case of in the form of box plots, you can also see the same. And on the right column, you can see it in the form of probabilities, how the probabilities changes. I should mention that on the first row, it's annual values, and then it continues with seasonal values, winter, spring, summer, and autumn. But the changes are the same in all the seasons, so lower values of wind speed and decreasing trends. Now I will move to precipitation. So again, I will start with change of devices. So in the past, we used conventional rain gauge, then we changed to tipping bucket, and newly we are changing to, oh, sorry, it changed. We changed to weighing rain gauges. Just to summarize up the results, we processed almost 1,000 stations. Almost 90% of stations were inhomogeneous. About 1/3 of breaks were explained by metadata. And in the last 60 years, long series, there were 2 to 3 breaks. In the end, to select stations suitable for the last normal, we ended with less than 600 stations. So 1/3 of stations had to be discarded during the process. And now some issues found during the process. The problem is that in annual time series, the difference between original and homogenized data is very, very high. It's almost 250 millimeters. The problem is how to explain this to customers when they come to buy the data, and how to explain them that it changed so much. And the problem is that the last period of automated measurements, it seems to be very underestimated. It has several causes. It has, for instance, causes in heating, when it evaporates almost half of precipitation during winters if it is not well set. And in summer, there is a problem with tipping bucket, that it's not able to change quickly. So generally, we have underestimation of the series. But the problem is that we have to correct to the last period, because otherwise, with new data in next years, it would not be comparable, and we need to compare new data when the customers want to compare it to the older data. The problem is also that the last period of automatization is quite short, and in the last 5 years, it was quite dry period, while the last year was quite wet. So there is big variance, and it also leads to the fact that it's very difficult to estimate the corrections in the right way. And in the end, I show here how the trends changes. So again, in blue, you see original time series. There was, if we take the whole 60-year period, there is increasing trend, linear trend. After correction, there is stable or a rather decreasing trend. But if you would look into 2 climate normals individually, so you would see 2 big decreasing trends. And I'm almost finishing. So again, comparison of the 2 climate normals. Blue is the older one, red is newer one. In case of precipitation, there is almost no change, but we have to take into account that, for instance, the beginning of this century, it was quite wet, while in the second decade, we faced rather lower values because of the drought that developed not only in the Czech Republic, but generally also in other regions. So thanks to the fact, when we see the long-term trend, there is no change. But we have to be careful that really the differences between the last 2 decades are very high. And in the last decade, it's not caused only naturally with the drought, but probably also with measuring, with automatization. So the last slide, conclusions. Influence of automatization, at least in case of wind speed and precipitation, is very high, and one have to be very careful when it is analyzed. In wind speed, we have big differences in calms and then in high speeds when we change to automatization. In case of precipitation, next to natural variability with drought that we faced. So there was probably also underestimation in the measurements. And to be a little bit positive, because those messages are not so happy. So the next steps are that the MetQC routines will be put into our package and made available for everybody. And because we are not satisfied with homogenization, or to be more specific, detection methods, detection of inhomogeneities, because there are some methods for multiple change detections, but they are not so user-friendly or available. On the other hand, there are user-friendly methods that are based only on single change. So we plan to revise all the methods and to create something new within this winter. So thank you for the attention, and that's all from my part.
Thank you very much, Peter, for a very interesting talk, and well done for the efforts that involve in this research, and that everything is actually free to use for the community. Some of the tools are available right now, and in the future, as far as I understand you, it will be for free as well. So now I would like to ask if someone would like to comment, to ask something, questions. Yes, please, Peter Domonkos.
Good afternoon to everybody. Peter, I was surprised with the big difference in the precipitation values. It is very unusual. And you told it is a fact that we usually fit in homogenization, we fit the time series to the last homogeneous section. It is a general rule, but I ask you that in special case, when you know that an instrument error causes a relatively large error, wouldn't it be better to correct immediately the values than to fit a known false, a known biased section, the older time series?
Yeah, you are fully right, and I agree with this. And we had some quarreling between me and Pavel and other colleagues, because the point is that here the aim is to estimate climate normal. And towards with normal, you will compare all the new data. So if we will estimate this climate normal in a wrong way, so all the comparison in the future will be wrong. From my point of view, I would be the happiest one if we could replace our automatization, because we really underestimate the series, and if we would be able to replace it with new measurements that would not underestimate, and then we could easily correct the last 5 or 6 years, and we would be happy. But unfortunately, it is not the case, or in the next short period, it's long term. But I fully understand. I had the same opinion as you, first to correct the last period, but it is not practical, unfortunately.
Thanks.
Thank you very much. Anita, please.
Hello, Peter. One question to your first part of the presentation, quality control. Do you have plans to do quality control on data in higher resolution than hourly, like automatically measurements in 1 minute or 10-minute data? Or do you have another software in use at your institute for that?
Yeah, it is a very good question. I mentioned it only very briefly. So far, it works very well for daily data, and we start to use it also for hourly data. But in case of hourly data, it needs to tackle with some not problems, but some special things. But generally, once it is finished, which now we run it in some provisional mode, but it's almost finished. And then it will be possible to use it generally on any sub-daily data, not only hourly, but in our institution, for instance, the basic time interval is 10 minutes. So we will use it also for 10 minutes data, and generally it should be possible to use it for any timeline. But the point is that in case of hourly data, we play with some smoothing of daily cycle and things like this, and we want to be sure that it works as best as possible. And also what I should mention, that we try to combine several methodological elements, because for instance, in sub-daily step, you can nicely see that temperature corresponds very well with wind speed and relative humidity, and yeah. So there are many things that we want to put together. But in the end, it should be very holistic approach, because if you generally, I'm sorry, I am longer now, but it's very important. If you devote only to one methodological element, you may find many things, but unless you compare it to other methodological elements and put it into the context of general weather, what happened in the day or within the part of day, so you may not be sure, and automatic running is then not dangerous, but not so straightforward. So we try to combine and try to combine several methodological elements. It is very important.
Okay, thank you.
Okay, Jose, please.
Yes, thank you. Yes, moreover, over this discussion, just to comment that with Climatol, my experiences with sub-daily data is that the problem is for estimating missing data is very difficult, because relative homogenization or estimation of missing data from neighboring stations relies on synchronization of the data. And with such short terms, high frequency, and then it's very difficult that a station which is only maybe 1 kilometer apart to have the same the ups and downs in the series will not be the same in one station and the other at the 10-minute scale, or even at 1 hour. Even, for example, for daily scale, for precipitation, you can find that the daily data are not well synchronized in the case of passing fronts, because some stations will reach the front will reach them one day and will reach the following stations the following day. So you have these problems even with daily data with precipitation. But anyway, in spite of this, it's very successful in identifying breakpoints, even in sub-daily. So for correction of inhomogeneities, it's perfectly validated. I have tested it on 3-hour synop values or in hourly. There is a publication about hourly temperatures in Romania, which was using the Climatol method, that it worked quite well. Thank you.
Thank you very much, Jose. Are there any further questions, comment?
I would have one comment
yes,
to
please.
What Jose mentioned. In the case of precipitation, it's very difficult to run any detection, either in case of daily or sub-daily data. I mean, you can detect something, but the question is how it is close to reality. So in case of precipitation, we try to combine our results with radar measurements. Because also in daily data on summer months, without radar data, you may not be sure what you get some detections, but you are not sure if it is correct or not unless you see the reality.
Yeah, the detection we do it with mainly with monthly data, but then the correction can be done at the daily or even sub-daily. Yeah.
Yeah, but are we speaking about quality control?
Well,
in case of detection, in homogeneities detection, you are right, but in case of data quality control, our experiences are that if you analyze monthly means, so the errors on the daily or sub-daily levels are masked to big extent. So you are able to detect only small portion of real problem. So in case of quality control, it's needed to work straight with measured data. Even daily aggregates also are able to mask many problems. So the best is to run hourly or minutes data.
Yeah, that was my opinion really also. But I had a surprise while homogenizing daily precipitation from a Texas area or with cooperation with somebody from the Georgetown University. And I found I didn't detect outliers in the daily precipitation values, but then in the monthly aggregates, there was an outstanding outlier. And I said, how is that possible? I had the same opinion like you. It's at the finest resolution that you can detect the errors. And it was because Climatol does not apply a test. It is not focused on quality control. It has some quality controls, but it's not perfect program for quality control. And I did not apply the detecting the repetition of values during several terms. And so it happened that in the database of NOAA, there was 17 days with some amount, I don't remember what, it was in inches, but it was not an outstanding value for 1 day, but repeated during 17 days, it gave an extraordinary amount of monthly precipitation. So it was detected better on the monthly than on the daily. That was anecdotic and exception. It happened.
Yeah, we also had such special case, for instance, 0 values in sunshine duration within the whole month, and in daily scale it was not detected because it was, I think, in winter, but in monthly scale it was detected. So yeah, there are some cases that really worth trying in monthly scale.
So one must look at every scale and every possible hint on the quality of the data.
Yeah, but in our MetQC routine, we take special care about these repeating values and also to duplicated values with neighbors, because it's not quite frequent, but it is frequent, and yeah, it's good to clean the problems before normal quality control.
Yeah, okay.
Thank you very much. Before we will end this session and go to our discussion session, Peter, I would like to ask you, do you think this MetQC, which is sounds like a very powerful tool, can be implemented on a real time or near real time?
Yeah, it is how we run it, because we run, for instance, drought monitoring system for the Czech Republic, but not only Czech Republic, but also Slovak Republic and generally Central Europe. And before we start with calculation of soil moisture and things like this, so we perform this quality control on fly. It's very quick and it works.
Okay, thank you very much. I see that Peter would like to add something. Please, Peter.
Yes, so practically I continue the last discussion about the quality control of precipitation, which was also presented this topic by Vincent, and was a question that how we could extend a monthly quality control to daily. So all these aspects, it is much easier to detect outliers in monthly scale. It is obvious for the large spatial and temporal variability of precipitation. So for instance, in my homogenization method in ACMANT, relatively the precipitation time series has the least quality control, special quality control, because physical outlier filtering occurs, as it is normal. It is more risky, and particularly risky when we homogenize daily data embedded to a homogenization procedure as Jose also spoke about this embedding to a homogenization procedure and outlier filtering is not fully correct, because we should control more the possible outliers. It mentioned also better that we should need radar data or other kind of data to control possible outliers on daily scale. Anything may happen. So I wanted to add only this, that we must be careful. Yes, we can make quality control on daily scale, but it is more than applying other thresholds than for monthly data.
Okay, thank you very much for a fruitful and very interesting discussions. So I would like to thanks again to our three speakers of these sessions, and we had time to make a quick discussion, general discussion. If someone would like to raise any subject or comments, you are more than welcome. Okay, so I would like, with your permission, to take this talk about quality control to the future, to the near future. And I would like to think or to know, how is your data undergoing quality control procedure these days? I'm meaning, do you purchase or subscribing to a licensed software? Or maybe you are developing your own algorithm? Or do you use an open source software? Or maybe you gain some experience with applying machine learning algorithm or any other kind of idea. In order to answer this, I would like to pass a quick survey. If you can please go to this link and just choose your answer or your answers. And in a minute, we will share with all of you the results and try to discuss on them and to make a short discussion. If it doesn't work, you can go directly via Mentimeter. I will give you the link as well, and just to enter the code, and you can answer the question. Okay, now I will share with you the results. I see that. Okay, Thanos, can you hear the slide?
The slide is very clear, yes.
Okay, so if I'm not wrong, and I see that most of us are using a self-developed algorithm or an open source, and just some of us paying for a licensed software, and other another doing something else, or maybe some kind of a combination. So this is interesting. And I can learn from this result that most of us are probably implementing some classical statistical methods. But how do you imagine the quality control procedure in an era that is characterized by rapidly ever increased amount of data? We are receiving data not only from automatic weather stations. Data can come from satellites, from radar, from ships that we just heard in the previous lectures, from airplanes. Every takeoff, every landing, we are getting the atmospheric profile, radio zones, even from our cellulars, from our mobiles. They apparently can measure some meteorological elements. and more even videos, camera videos that are spread in our cities, in the rural area, or whenever they located. So we are talking about big data, and we're speaking on data assimilation, a real-time data assimilation. So how can we bring all this data into account in order to improve our monitoring and the quality of the measurement? Should we try to apply some machine learning algorithm that can handle this big data to look for anomalies, or we should stick with the classical statistics, which we are the user, the expert, define the rules based on our knowledge, based on the physics, statistics, mathematics, and so on. So I'll be more than happy if you can share your thoughts with us. Thank you very much. Yes, Thanos, please.
I hope that you'll be able to hear me.
Yeah, we're hearing you loud and clear.
The question is a bit different. It's addressed to meteorological services. Because we are a university laboratory, so we have only one station. So we are not confronted with all this mass flow of data that you described.
We can't hear you, Thanos.
Yeah. I say our lab has only one station. It's easy for us to handle the data we are getting. I think the question is much more crucial for meteorological services like the one you work at. I would like to hear people working in meteorological services. They intend to plan to proceed and to tackle.
We barely heard your last sentence, but if I understand you correct, you said that it's not an academic issue, maybe it is more relevant for meteorological services.
It is an academic concerning perhaps the algorithms to be embedded. But the problem is not mainly for academic institutions because they have to deal with a rather limited number of data flow compared to meteorological services.
Mm-hmm. Okay, thank you very much. Barbara Chimini, I saw you raising hand, something?
I just would like to know what the experience of those using an AE algorithms is so far.
Yes, I think it will be interesting if someone that applying AI, machine learning algorithm, to share it with us, and those of you that choose other options, it will be interesting to hear your opinion about it as well. Thank you.
Maybe can I comment this a little bit?
Yes, sure. Please, Peter.
We run quality control in two ways, either for operational data, when we want to be sure that other processing like that drought monitoring I mentioned is all right. And in that case, if we detect any suspicious values, so we disregard it from other processing. But then there is a second layer. And for instance, at Czech Hydrometeorological Institution, there is a good database system, Data, that itself provides tools for manual quality control. But what we try is to create inputs that will help, that will focus the manual control on the problems, provide them with other information like from other meteorological elements, put everything together, maps and graphs, but in the end, it's solely based on judgment of individual workers if they decide to correct the data. Here I'm speaking mainly on daily scale, but we try this also on sub-daily scale, like in 10 minutes data. So I mean, so far, it's my opinion that there is still no final solution in the sense that you could run automatically quality control and just to be happy you have results and not to do anything else. My opinion is that still methodological services that guarantee the quality of data should still make some manual stuff around this.
Yes, you are probably right, but if I'm thinking on the near future, this can be an advantage or disadvantage when you are having lots of data, because some of it is wrong for sure. But I think that machine learning algorithm can detect this false record and delete them, and we will get a more special cover of measurements. And finally, I think that it will be more accurate because you are using satellites, you are using radars, you are using cellulars and chips and whatever, any data is playing inside this game. You just need to make an order in it and to extract the correct signal, which will help us to make a better quality control, and finally to use a better measurement in order to detect climate change, to calculate climate normals, and for any other purposes. Okay, any other comments?
You mentioned before the assimilation, the word assimilation.
Mm-hmm.
I think that all models that are assimilating all this kind of data are introducing these quality controls, which have into account that the data must be consistent with the state of the atmosphere determined by the other observations. So it seems to be a rather robust method for quality control. Maybe all things can be improved, of course, but there is already something, I think. I'm not a specialist in this field, so I just comment.
Okay, thank you very much. Are there any other comments before we are ending this session? Yes, Peter, please.
I agree with you that the tendency is that will be even more automated the quality control, but it is only a tendency. So still there are problems in small special scales and small temporal cases in which we still nowadays we need manual works. So both sides are right. And thank you very much.
Thank you, Peter. Yes, Dan, please.
Yeah, thank you. At the UK Met Office, I think we do quality control for a number of different purposes. So we have one team that is responsible for the quality control of the in situ data in our main climate database, and you heard a presentation from Callum before the break. He works in that team. I work in a team that does climate monitoring, so we are users of the data, and some of the products that we produce, we try to produce in near real time. So before Callum and his colleagues have been able to carry out the formal quality control. So we also have some tests that we run in our software, and as you say, the volume of data is increasing. So we are trying to automate some of those tests, and we are not trying to replace the work that is done as part of the formal QC process. We are only trying to improve the products that we produce, such as the maps, for example, that go onto our website. And so we are trying to identify in an automated way bullseyes within those maps. And so one of the things that we have experimented with is looking at the curvature of the gridded field. So we are interpolating the station data to a regular 1 kilometer grid, and then looking at the curvature of that field, and then identifying areas, then looking at the curvature of that field at the location of each station to try and identify a station that may be causing a bullseye. We are still experimenting with this and trying to calibrate that approach for different variables, monthly data, daily data, temperature, rainfall, etc. So it's better for some things than others, but we certainly realize that for our application, we are a small team, and we can't do in real time all of the manual inspection that is done in a more formal process. So, and I think experimenting perhaps with some machine learning, pattern recognition type things that come from other fields. So sort of all the image processing field, I think, would be very interesting, because essentially our grids can be thought of as an image. And I think we could potentially learn something from that, but as I say, not trying to replace the more formal process, but trying to find something that is applicable to our particular use of the data, I suppose. So yeah.
Great.
Okay,
Thank
thanks.
you very much for sharing it with us. And I would like to thank you all for being actively during this discussion session. And Thanos, the floor is yours.
Thank you very much for sharing this session. We'll meet tomorrow again at 11 o'clock. Have a nice end of the day, or depending on the time zone you are at. See you tomorrow. Bye-bye.
Bye-bye. Thank you very much.
Bye.
Thank you all for your participation.
Thank you. Bye-bye.
Bye-bye.
Bye-bye. Thank you.